And again, we'll talk about microwave spectroscopy, Schmid, It's like
Okay, so now I can hear me. Okay, well, first of all, thanks for the organizers for this real March meeting. So I'll be talking about very old stuff, Schmid transition. So I guess that it's so old that for many people it will be entirely new. So the original results, mini results, are done with Manfra, who is in Grenoble, and there are some ongoing stuff that we're trying to clean up with Lat Krylovich, who just graduated and left Google Quantum, and Benji Remes, who is a postdoc at Yale. And there are two papers, or paper and preprinted published, but there's some other stuff it will mention. But again, so thanks for this opportunity to kind of look back. And to be really kind of really back. It's not as far as the case of
your mic is not working.
Oh, really? Oh, somebody else should put it higher. Let me try. How about now? Is it better? Okay, good. Yeah, so it's not as old as Alexander was doing just all back to 20s, but still 80s. So I'll tell a little bit about the MQT and Schmid transition. It's 80s, and then about a few things about experiments in DC current domain, and it's 80s to 2000. And then there was unexpected revival of this stuff coming basically as an offshoot of qubit technology with superconducting devices. So that's around this time, and there are some controversies to tell about. There'll be some original part, which is essentially applying of all the standard machinery of light measure liquid, basically, to or quantum impurity to this kind of problems, and which allows to understand, I think, quite easily what was observed so far. And there is some outlook that I'll hope to get at the end too. So, well, Leonid was mentioned several times here, and he likes very fundamental questions. So there was a question about whether a macroscopic system may tunnel. And this question actually, I think that I don't know who first proposed it, but Leonid definitely had a single author remark about it. And then he suggested to look at a squid or a small junction as a test device where the collective variable is just a phase across some junction. It's a variable that responds to for many electrons, and ask whether this phase may tunnel. And basically, the model he thought of is current bias Josephson junction. So phi is a phase across the junction, and I is current, which somehow mysteriously you can induce despite no leads. And there is a resistor that shunts this junction, and it's a dissipative element, whatever it means. And then this model, Caldera-Leggett model, suggested a model for the system. And basically, this is trivial part. This is this guy, which is coupled to something that is called reservoir. And basically, this reservoir was introduced to describe a possibility of tunneling with dissipation, so that energy goes into this additional system due to some coupling of the coordinate phi, which became q, and the reservoir. And here's the model. So the coupling between our degree of freedom, macroscopic degree of freedom, and And the system was basically coupling between Q and coordinates of a bunch of oscillators. The oscillators had some continuous spectrum. The strengths of couplings depend on frequency of oscillator. And this 1/r basically was mapped onto this combination of the coefficients of the model. So it's a resistor in a dissipative sense, so there's no weak localization, no any kind of localization, no coherence effects. It's just what people call a buff. Okay, so it's able to absorb energy, it's able to give energy at finite temperature back to the system, and also it's a source of quantum fluctuations. So with this model, there was prediction that the particle may tunnel despite dissipation, and somehow tunneling rate will depends on the resistance. But the main thing is that you go to 0 temperature, activation is over, and still have some tunneling. And that was kind of a revelation at that time that the Josephson junction, very nice quantum system that actually behaves like a classical thing, just cos phi, actually is not ideal, and you can tunnel from one minimum of cosine to another if they are biased from one perspective to another. But there were a number of experiments, and I would say definitive set of experiments were done by these people. And here is a curve basically that tells the story. So basically, this is escape time from this minimum to something else is a function of temperature. And here is activation. But eventually it veers off. And if you have an imagination, you can continue this horizontally down to 0 temperature. And this is this quantum limit. So this is the probability of tunneling rather than activation. And they analyze it as a function of resistance. It all kind of fit well this MQT theory. So there was not much of contradiction with it, and things were pretty clear. And then in parallel, or slightly, it's 81, 83. Schmid came with interesting suggestions. So let's just unbias the junction. Albert Schmid suggested that we just remove current, and then we have two identical minima. Okay, and the question is that if you start with a phase in a given minimum, whether this phase will always stay there or will move away, kind of diffuse away, right? And again, it was pretty formal paper, action, and then analysis of the action and some two limits. And basically, Albert's he did lots of good things. So one thing that he returned from Q to phi, and this is really this qubit story. I don't know. It's charging energy of a junction plus Josephson energy, and he expressed these elements all back in the very nice quantity, which is resistance measured in quantum in units of quantum resistance, h over squared. And here comes the phase diagram where he was able to define the 2 points by some duality argument that separated localized phase at small resistance, so at large nu, eta, sorry, from delocalized phase that corresponds to large resistance, respectively, small eta. Okay, so he wasn't able with his method to draw a line, and he conjectured some point in the middle, some mysterious fixed point. So this was all the diagram that he plotted. So it's Albert Schmid, 83. Then Bulgadaev, a year later, I sort of remember. I mean, okay, so I looked at the paper. So basically, all he did, he just straightened these lines and said, okay, actually they go vertically to start with, but still, this point is still there. And just it's from his paper. So it was still not clear. I think that really a beautiful paper for that time was Pakagine's paper 85, where from considerations which are essentially RG group, RG considerations, he was able to tell, okay, it's a straight line, just a straight line connecting these 2 points, and there are 2 phases independently of this parameter S that knows about the properties of the junction, and everything depends just on the environment, on R. The system either has localized phase or delocalized phase. So the key point here is that independent of the parameters of the junction, there is a localization transition. It depends only on the environment, on the resistance of the environment compared to quantum resistance. Okay, so clear-cut, beautiful statement. Now, so the only thing you know how to check it. So the thing is that ideal system would be a system without any lead attached, because basically the statements of all these papers are about the correlation function phi of t, phi of 0. And the statement that I just made in words here is in formula. So if initially phi of 0 is close to some 2 pi n, then localization means that it will be forever staying near that minimum. So this correlation function is confined, okay, less than pi. This is localized phase. Rather, and conversely, if this correlation function grows with time, it's the confinement. The phase drifts away here, right? So, but to have this system without any attached leads and measure something at that time in 80s was impossible. And what people resorted to is to attach leads to this thing and try to measure something more complicated. So now let's maybe drive this point about transition a bit deeper. So let's look at a single junction. Okay, it's as simple as that, just single junction. I also allowed myself to add some kind of battery and capacitors to allow some charge bias, basically polarization. It doesn't hurt. So this polarization charge will be here. This is the charging energy projected on the low energy subspace where no quasi-particles. Everything is in ground state, right? So this is just Johnson energy, and this is charging energy just straight from the high school textbook. It's q squared over 2c written in some weird way. In terms of the charge iterator, which is 1 over IDD phi, and this shift and the polarization charge. Now, terminology, the current qubit terminology is that if EJ over C is small, it's called charge qubit, and if EJ over C is large, it's called Transmon for some reasons. And this actually is the devices that make civilization run and give some work for Simon Trebst and other people that do fancy stuff. So now, even at large EJ over C, okay, still for this system, phase will not be localized. You can recognize in this equation basically a single equation for Bloch electrons, okay, in 1D. And even in tight binding, there is still a band, right? So even if it's tight binding, still I put a particle at some minimum and it will diffuse away, or okay, it will spread away. So so in this respect, even if it is large, still the phase is not localized. It is counterintuitive because this Transmon again is a basis for this whole technology. But the thing is that it's based on technology for much higher frequencies. It's not a question about slow motion of a phase away from the given minimum. It's a question about transitions between levels that are defined basically by the plasma frequency, by the square root in JC. Okay, that's very different. We'll get back to it. So now, again, if I look more carefully, so for isolated system, there are bands, right? And the lowest band is most tight bounded. Next one is wider. You can calculate all this widths of the bands. It's straightforward semi-classics. And basically, going actually to Rockwell-Stock, so capacitance is just second derivative of energy with respect to the polarization charge. So basically, if I take second derivative of this energy at n equals 0, I'll get capacitance by definition. And if inverse capacitance, sorry. And if the band is narrow, then capacitance is huge. So basically, this thing at low frequencies is a huge capacitor with capacitance which scales proportionally to 1 over lambda. And lambda has its exponent. Okay, so it's a capacitor, but with huge capacitance, not a superconductor. It doesn't conduct electricity because nothing is attached to it. Now, so the thing about this shunt is that, and this is a result basically of all this works, that the bandwidth gets renormalized the renormalization depends on the resistance with respect to the quantum resistance. And at k equals 1/2, there is a transition when the band is collapsing. So there is a bandwidth at k less than 1/2, and it collapses at k equals 1/2, and that's it, right? So the prediction is that at k equals 1/2, there is a transition from insulating state where there is kind of a supercapacitor to a superconducting state, whatever it means. So now, once again, so what does it mean? I mean, to see it, one needs to somehow the best thing would be to measure linear response. But if you want to measure linear response at DC, you have to attach leads. And there is a system of problems. So first of all, you have to have this guy to be flat in frequency. So this resistor actually is impedance, and impedance must be independent of omega r at all frequencies. Ideal measurement is linear response. It's difficult to do DC without leads. So okay, if you attach leads and you do nonlinear response. And that's what was done in between the 80s and 2000. I think that most clear summarizing paper is this one. So they had some small current, and they basically looked at MQT and tried to, to infer what happens at I equals 0. And the points were all over the place. And here is this basically defining paragraph, at least for me. So the prediction that Johnson junction remains an insulator even in weakly dissipative environment and in the limit of Ej over C to infinity is difficult to confirm. And it's difficult, again, because of what I said, that you have a very, very narrow band, and somehow you should be very gentle with the system to see these delicate effects. So, and then basically this subject sort of died. Yeah, please.
But for any non-zero current bias, it's always, it's always, well, then you get.
Yeah, for non-zero bias, there is some, there is some voltage. Yes.
Right.
So if you have finite current,
you don't need a critical current to.
No. Exactly. Yes, that's a very good point. Yes. Yeah. Exactly. That's perfect. So this is at currents that are, I don't know, 10 to minus whatever critical current of a junction. It's tiny currents. System is still dissipative.
Mm-hmm.
With tiny leakage. So voltage is very small, but it's there. Right. So it's dissipative, very weak, and you have to look at the limit of zero current. And then kind of this subject reemerged with the development of high frequency microwave measurements. And I don't know, maybe it's effect of COVID, but this paper appeared, and you can absence of, so just in your face, there's no mid transition. And basically they looked at the high frequency counterpart of what Leo asked. It's admittance at high frequencies, and this admittance was depending on some fluxes. And their point was that okay, if there is a dependence on flux, there is superconductivity, and just there is no transition. So we'll get back to it, and I'll tell about this paper a bit more. So that was one paper. Then there was another paper, very recent, where actually there was statement that this transition was observed. Okay, and then there are papers that were kind of tangential to it, because in addition to charge transport, you may look at heat transport through a junction, and that's a specialty of Yuka Pekala. And there was actually, I think, a very nice paper experimentally with conclusions that I couldn't decipher, because it says charge transport is expected dissipative, and then but nevertheless somehow ambiguously demonstrating that the supercurrent survives. And I just my English was not sufficient to understand. And then I mean, sure enough, this experiments interesting, and there was the theory. So here, absence versus presence. And you can see from this diagram actually that it's pretty different from Schmid, right? So Schmid is here, and that's what they predicted, or actually derived in a way with combination of analytical and numerical arguments. So And it caused the interesting exchange between various people, these people and this, that challenged the numerical procedure. But from my point of view, I mean, okay, you can go back and forth and try to understand what it means. But what to me, alpha equals 0 is just isolated qubit. That's what I started with. It's isolated system. So how in the Earth you can get finite conductance for something that is not attached to anything? I just don't understand. So this part is just logically is not reasonable. So that was the problem. And so now I'm coming to basically next point of the discussion of the Schmid transition. So 2 + 2 statements. So the old ones is that I just already said that the transition is independent of the local properties of the contact. Now Sabir's here. Okay, good. So it's a transition only at 0 frequency and 0 temperature, and it's a quantum phase transition, and at any finite temperature, it's a crossover. Yeah.
So you said before that there was a wonderful RG by Paco Guinea. What's that? Present paper is saying that RG is wrong or what?
No, Guinea's paper I think is right. I mean, everything is perfect, and
But I guess conclusion is different.
this conclusion is right.
Uh-huh.
And this conclusion is wrong.
Thank you.
I try to be polite, but okay. So let's close that. I mean, that's and again, I talked to Masaki at some point. So when I was preparing this talk, I realized what Masaki meant. I mean, there is some irrelevant operator in some Hamiltonian, and there was kind of a justification of possibly something going wrong. And I'll come to this irrelevant operator. Indeed, it's important for something, but not for the conclusions of this paper. Right. So basically, these are kind of simple, clear statements, and it cannot be a transition at finite temperature, finite frequency, because basically, it's a harmonic system with a nonlinearity in one point. So it is a kind of a very marginal situation. You cannot have transition at finite temperature, finite frequency, crossover. Now, the question is, how you probe it, and that's the new part. So basically, what happened with this new experiment that one should look at different response functions, and the wonderful response function basically is the admittance, or even better, the reflection amplitude of the junction. And there is full scaling function that one can find. And you can observe the full scaling function on different sides of the transition with different devices, not with the same device. And on one of the sides, the spreading side can be done only with charge qubit, and another side, insulating, may be done or can be done only with a transmon, and no other way around. And one more thing, this last new statement, that basically this real and imaginary part. So there are 2 functions you can try to scale. And they scale the same way only in this interval around k = 1/2 around transition, and outside they scale in a different way. And that's actually basically this least irrelevant operator that Masaki perhaps had in mind. So now basically these new experiments started by Vladimir, who was actually a former Yale graduate. So he managed to do arrays like more than 10,000 junctions, which are incredibly coherent. And they provide this environment, almost ideal environment, that has almost flat z omega, because basically all dissipation is just sending plasmon waves down the line. And this line at the end has this junction, or squid, if you want. So here's the schematics. And what he's able to do, what they're able to do, is to send a wave and measure the reflected wave. And that gives it just directly the scattering amplitude with real and imaginary part. That's it. So, and you can translate it into some circuit engineering terms, which also they do. And there is a relation between the admittance and scattering phase. So I will be operating just the scattering phase, and it has a real part and imaginary part. The inelastic cross section is associated with the imaginary part, of course, of scattering phase shift. And basically, the statement about Schmid transition is very simple. So at k less than 1/2, the response is purely capacitive at 0 frequency, and this is capacitive response. And in other phase, superconducting k larger than 1/2, zero frequency response is purely superconducting. Its reflection is -1 and delta is pi/2. That's it. So this is a delta versus k at omega equals to 0. And the point is that if you take transmon, then the crossover at finite frequency, if you take a transmon at small but finite frequency, then crossover between small phase and large phase occurs at k less than 1/2 for this device. And for charge qubit, it occurs here. And basically, that's why you can observe the entire crossover as a function of frequency for transmon at k less than 1/2 and for charge qubit at k larger than 1/2. So as simple as that. It's just where the crossover comes for different local EJ over C values. So the rest is basically very simple math. So one more thing that I would like to emphasize that I will use at the end, which is coming soon, that basically this qubit also has higher levels, and there is a transition within the qubit. Suppose just expand it to phi squared, then it's harmonic oscillator, and there's transition between 0 and 1 state. And this transition is in resonance with some mode in the transmission line, so it's getting broadened, and it's experimentally measured. This line of the qubit actually broadens up due to the connection to the waveguide, to the array. Now, if I want to look at low frequencies, basically I can project this Hamiltonian onto the low energy subspace, and then this guy will just translate into sine Gordon. But mind you, the sine Gordon with respect to the charge rather than the phase. So we started with the Josephson cos phi, and now at low energy space, in low energy space, it's cosine of n, the charge transfers through the junction, and lambda is exponentially small in EJ over C. Now you can also just force it into the standard sine Gordon form, basically going back from momenta to some fictitious coordinate x, and basically this guy is just some impurity sitting at the end. So that's why it's boundary sine Gordon, and usual commutation relation between phi and theta. So that actually sets up the problems that you can do the standard things, and you can just analyze first perturbatively in lambda. See that the phase has this form, the base of phase and frequency has this form, and several simple observations. First of all, the phase is partially dissipative. At any frequency, it has some dissipative part. Now, at k less than 1/2, there is a crossover frequency, which has this lambda to power 1 over minus 2k dependence, and at k equals 1/2 it collapses, as one should get. And the sign of this difference at any frequency is negative, meaning that the response is capacitive. Now at k larger than 1/2, the response is purely inductive. So that's already the harbinger between the two phases, and basically one can do another limit by proper going from one fixed point Hamiltonian to another one, and I will skip the standard details here. The only one thing here that again it goes back to this Masaki's remark. So if you try to look at what happens with the exponent 1 over k minus 2 and send k to 0, you'll get delta of omega scales at very high power of omega, and that would correspond to super capacitive response. So it will be not that impedance scales as omega c like in Rockwell talks, but some omega to power infinity, which is impossible. And that's basically the reflection of the fact that when you calculate imaginary and real part of the admission, the fixed point Hamiltonians are the leading terms in the fixed point Hamiltonian are somewhat different, and this difference comes only at k less than 1/3. So that's a small caveat. Apart from this, everything is very standard. Now, also with a pure, with a current knowledge about sine Gordon, you can also find all the coefficients with numbers, and that's just tedious but not complicated. And basically, you can find the full crossover and see that the inelastic scattering is maximal around the point where omega equals omega star. One more thing interesting is that at the transition, at least theoretically, the scattering is almost, actually not almost, but entirely inelastic. So the non-dissipative part of scattering phase is just 0, and it's purely inelastic. It's only I. One can do by duality a charge qubit, and again, it's tedious but not very interesting. So now I just what is the experimental outcome, or how we can understand now the experiments. So basically, the experiment that I mentioned, both absence of the transition and presence of the transition, it's the same, well, more or less the same circuit, where small junction is replaced by a squid, and you can change the effective Johnson energy of the squid by threading a flux. Okay. So now I just look at one of the equations that I have shown, and it's perturbative equation for delta of omega. And as you see, the delta of omega depends on omega, but the coefficient depends on this crossover frequency, which in turn depends on the J, which in turn depends on phi. So this coefficient depends on phi. If you measure at finite frequency, then there is some dependence of omega, just because of this prefactor. So you really have to go to low frequencies to see something, to make a definite statement. If you don't, you just see some dependence of phi. And that's exactly what was seen in this paper, which claimed absence of the transition. So they interpreted the flux dependence, which must be there, as the indication that there was no transition. Now, can you, in this kind of measurements, see that actually maybe there is a harbinger of transition? Maybe there's not transition, but maybe one can expect transition. Then you look at this coefficient, which is only k dependent, and as you can see, it changes sign at k equals 1/2. And that was the thing, the clever thing that this other paper did. So here is a dependence of the phase shift as a function of some parameter that basically controls k. Okay, it calls also flux, but it controls k. And if you can see that the maxima become minima, and that's basically the change, the flip of the sign of oscillations is a harbinger of the transitions. So here it's in a bigger scale, and that we already discussed. And one more thing, that the inelastic cross-section function of omega becomes flat, and it sort of flattens at k approaching 1/2. I mean, okay, it's not perfect, but at least there is some indication of it. So that's why I talked to experimenters that's still in the process. They also didn't try to analyze simultaneously real and imaginary part and see the scaling simultaneously for both parts. Now, another thing that you can you do is also shine some light that would cause transitions between the qubit levels, so between 0 and 1, and then allow photons to be emitted. So it's kind of a fluorescence. And again, I'll skip details, but basically this process boils down to the following. So we first resonantly excite qubit to level 1. Then this excited level kind of shakes up the junctions in the chain, so shakes up plasma excitations, and then it emits a photon, maybe at lower energy, because some energy was lost to this shake up photons. It's like in the Magnetotransport catastrophe, basically, or X-ray singularity physics. And what happens is that you shine omega 0 as a junction, you get some omega prime going out, and some low energy photons that you even cannot detect. And if you just iterate over them, then you can find this inelastic scattering cross section, and the harbinger of transition would be that at k equals 1/2, there is certain specific exponent for the inelastic scattering rate. So again, it was not measured. Something more crude was measured, and there is a reasonable, to the level of experimental accuracy, agreement with theory. So we'll not discuss that as well in detail. Now, last thing that maybe in the next few minutes is that one can do the following thing. So I go back to this Hamiltonian in the low energy space, and then let's drive the charge by DC current. So I attach also leads now. So that's like Bloch oscillations, right? So you drive the quasi momentum along the Brillouin zone. It's not new. These two papers, and actually this guy even correctly guessed that something should happen at Bloch at Schmid transition, although there was no explanation of what should happen. And basically, if you just use the same machinery that I just described, what happens basically is that, okay, you drive your junction, Now this Bloch oscillations mix up because of nonlinearity of the system with 0-point fluctuations of the Latinger liquid, and you emit photons at all energies. And the emission spectrum is here, and we can find the spectral. Actually, it's not narrow at all. It's pretty wide. Wasn't observed yet. Now one can look what happens then to IV characteristic, and that goes back to actually Leo's question. So basically, if you emit energy into waves, then you lose energy, right? So there must be some dissipative resistance just because you lose energy. And you can just calculate it the following way. Just write I dot V equals dissipated power. You can find emission power divided by current, you find voltage. That's what is done. And basically, you can find the characteristic. And now the big picture is that all this kind of cute effects happen in a very small region of current, way below the critical current of the junction. So it's slightly dissipative, and all these effects are tiny. Here's the scale. Now, next thing, if you remember the Shapiro step, so basically you can synchronize any oscillation with external source, and you can synchronize Bloch oscillations with external light shining on the junction, and it will lead to some structure in IV characteristic, which is like Shapiro steps, but in dual variable. Again, we didn't invent it. It was back in this lecture's paper, but actually recently there were experiments that did observe it quite nicely. Although, again, according to our theory, the accuracy of the steps is way below that one would expect from pure quantum mechanics. So this is under the rug, and I'll not discuss that, although it's kind of cute. And I'm very towards conclusions. So basically, there's entire cottage industry of this stuff of quantum body physics with circuit QED. And these are like papers in the last year, basically out of 3 groups now, because it's also faculty. And there are earlier papers. Now, there are even more kind of out of this world things. You can create some bizarre lattices with hyperbolic lattices with flat bands. And there was a theory paper and some experiment. And you can also try to cook up some TRS breaking physics in cavity QED. And this is just theory suggestions, no experiments. And maybe it'll be sometime. So what is it good for? Back to Alex's comment to some other talks. So do we learn something new of it? Well, okay, so these kind of systems give you possibly give you clean manifestations of basic physics, like Schmid transition, and its extensions. So quantum impurity with internal degrees of freedom. It allows, in principle, to explore dynamics of chaos, which I didn't discuss, but there are some papers on it, and exotic states, or whatever it was. From my point of view, there must be 0 point. Most important that it actually allows us to hopefully understand better physics of relevant for applications. Parameters such as, what is the Q factor of these superinductors, these huge chains, these large inductance, and the linear elements that are actually important for circuit QED applications, and also current standards with Bloch oscillations. So that's basically the end. Thanks.
Questions?
Yeah.
Yeah, I may be confused, but I want to understand this point. So if you have just dissipation but no bias, no current bias,
Yeah.
then there's a transition, Schmid transition,
Yeah.
at 1 and 1/2.
Yeah, whatever. Yeah.
But if you now current bias it without dissipation, you would have Bloch oscillations. So now it seems like dissipation actually delocalizes you. Now it allows you to suck up energy and be 1 year, 1 year start localization.
Right. So if you,
am I confused about that?
no, it's a question of order limits, basically. It's a question of order limits. Yeah. So no, you're right.
There's some non-monotonic behavior.
Yes. Yeah. It's basically order of limits, and in a way, it's kind of epitomized.
Maybe it's
the second. I don't know why I didn't show up. Yeah, here. So basically, this non-monotonicity is basically what you're talking about.
Yeah. Okay, thank you.
Yeah. So with this, your limit basically, this thing goes to zero, all the way to zero, and.
Thank you.
If I recall correctly, the Schmid transition was for perfect coupling to this wire that connects to the
Yes.
resistance.
Yes.
What if you have tunneling and imperfection added? Does it change the statement?
Yes. Good. So. Right. So in the limit of zero tunneling, if it's just capacitive coupling, then just there is no transition because at omega zero. So it's you can, for any transmission, you can integrate out the external system and get an action of zero-dimensional system. And it's important this integration out what kind of impedance at omega to zero it brings. So if there is some interval of omegas where impedance is finite, not infinite, Schmid transition is there, and just a question about the value of the impedance. All right. So you make a tunneling, it's okay. So it's a I mean, how people
location doesn't.
No, I mean, how experimentalists tell is that it's important what impedance the junction sees, when it looks into the outside. Okay, there may be standing waves, that's okay, and as long as in the limit of zero frequency you have certain behavior of impedance, it works.
All right, so let's thank Leonid again. Our next speaker is Dmytro, who will tell us about linear and non-linear transport of the topological issues.
All right, I suppose I can flip through slides manually. All right, Sasha, thank you very much. And I would like to say that it's a pleasure to be part of such a lineup. So I very much appreciate the opportunity to speak. And today I'm going to talk about, again, an old subject. It's old by modern day standards, so it's about 20 years old. Okay, so I'm going to talk about the quantum spin Hall effect. And basically, there have been thousands of papers written on the subject. Okay, so I will not review all of them. So I'll try to just give you a sort of a brief summary of what's going on and what has been measured, and then we'll basically discuss to what extent one can understand what's been measured. So just to start with basic things and set up expectations, and some of the mental picture. Let's think about the artist rendition of a quantum spin Hall insulator. This is a two-dimensional phase, two-dimensional insulator with helical H states. So basically on each edge, does this work? It works when I turn my head, right? Basically at each edge of the sample, there are two counter-propagating states with opposite spins. They're time reversal counterparts of each other. Okay, so you can think about this phase as basically two quantum pole insulators with opposite Hall conductivities put sort of on top of each other. Okay, so the band structure, if you want to think about band structure, this is the characteristic band structure proposed by Ken and Millet. If the spin orbit coupling graphene were large, it would have been a quantum spin Hall insulator. So you basically have valence band, conduction band, and you have two edge states connecting these bands, and these edge states have counter, opposite slopes and opposite spins. Okay, so that's what you think about when you want to think about the band structure of this material. So what has happened? So I told you that there are thousands of papers written on the subject, but there are 2 to 3 orders magnitude less experimental discoveries of these materials. So I will go over essentially a substantial fraction of them. Okay, so the first one comes back to Mollenkamp's group in Wurzburg in 2007. Okay, so maybe I forgot to say one phrase here. So about the expectations, right? Given this setup here, we expect that at least for certain transport experiments, we'll have quantized electric transport, right? If you calculate some Landauer resistances, they will have some well-defined values. Okay, we expect sensitivity to time reversal breaking. So this phase is protected by time reversal. So if you remove time reversal, you will change something about this phase. You will destroy it. In particular, it's clear that application of magnetic field will affect edge transport because magnetic field can convert, spin up into spin down depending on the direction, of course, and so on and so forth. So sensitivity to time reversal breaking. You can ask me, this is quantum spin Hall insulator. Are you gonna measure, quantized spin transport or something like that? So basically, it's never done, at least as far as I know. So this current-induced edge spin polarization was measured in just regular, metallic spin Hall effects, but I do not know of measurements in this quantum spin Hall insulator business. Okay, so in the just classical part, it was measured by optically, essentially. Okay, so we expect quantization of some electric transport coefficients, and we expect sensitivity to time reversal break. And the recurring thing here will be that when you look at various things for the first time, everything makes sense. When you look at them for the second time, nothing makes sense, and so on and so forth. It's as always, you come to a field with thousands of papers written. It looks like everything has been done. Then you start looking into this, and not everything has been done. And as always, okay. So the first paper is by experimental papers by Mollenkamp and company, basically show that in long channels, in long samples, long means a few microns, 10 microns, basically, there's really no quantization. Okay, even down to lowest temperatures. In short channels, there's quantization. If you look at these curves, logarithmic scale with sort of mother's eye, you can call this approach to some quantization. Okay, but good enough. This is a difficult, extremely difficult system. Okay, so fine, you do see quantization in short samples. You apply magnetic field. And then you see the expected thing, right? You increase magnetic field, the conductance goes down. So here you notice that the magnetoconductance was measured actually for long samples without quantization of some conductance. Okay, so here comes the I guess three weird things about these magnetoconductances. The first thing you notice is the scale on this b-axis. It's 0.05 Tesla. It's a very, very small field. Okay, of course, if it's a very, very small field, this slope, the initial slope of the magnetoconductance is very, very large. So in other measurements, you'll see that it's almost a cusp at zero magnetic field. Okay, so small magnetic fields suppress conductance. It's almost cusp-like at small magnetic fields. In this particular case, there's also a strange situation. I told you that if magnetic field is perpendicular to edge spin orientation, the effect should be the largest. Here, it's actually the other way around. When it's parallel to the edge spin polarization, the effect, the suppression is the largest, and it's nothing basically when magnetic field technically perpendicular to that edge spin polarization. So one of the explanations for this was given by Schuch and Zhang's group. They said, there's a bulk inversion asymmetry in the sample, so it kind of converts this magnetic field into matrix element of something like this magnetic field, and it works. Then they took this idea, ran numerical simulations of this material, got something that they called looking qualitatively like the experiments, and qualitatively does, except you notice the scale for the magnetic field, it's half a Tesla instead of 0.05 Tesla. And in order to get this sharp drop, you need a disorder strength that's several times the gap of the material. So it's enormous disorder. Okay, and even with that enormous disorder, you don't quite get to this. Okay, so there's something going on here. Okay, so let me now go forward by a decade, by 10 years. Okay, so experiments on monolayer tungsten ditelluride came. Okay, so this is a material, a monolayer material with probably much stronger correlations. Okay, because of 5D orbitals of tungsten. But just by way of describing observed things, again, the work on short channels came from MIT, from Pablo's group, and they did see that as a function of gate voltage, you sort of, again, have quantization of some appropriately defined resistance, okay, presumably when the chemical potential in the gap, now of course it drops. You see the length of the channel here is, less than 100 of nanometers. Again, the magnetic field dependence of conductance is what you expect, right? Magnetic field drops the conductance, except it saturates for various values of B. It was basically ascribed to puddles, existing charge puddles close to the edge. Sometimes it saturates, sometimes it doesn't. This is a function of gate voltage. Okay, so and then I would like to also mention the experiments on the long edges. So those edges that I just mentioned are 100 nanometers long. These are couple microns long. Okay, so here there is absolutely no quantization of conductance at zero magnetic field. Conductance is strongly suppressed. Okay, and then at finite magnetic field, the conductance is suppressed. This is a function of angle between magnetic field and the polarization of the spin on the edge. You see it's, again, fairly strongly suppressed, not as strongly as in mercury telluride, but on the scale of, 10th of a Tesla, the conductance goes down appreciably. So this is actually, non-trivial observation, because in the bulk part of the system, say you dope it or you increase the temperature, the magnetoconductance is just zero. It just doesn't exist. Okay, so it's very, very, very strong dependence of conductance on magnetic field. Okay, so finally, just to mention a very recent paper, so you see that this is a very much lively subject. There is a recent preprint where quantum spin Hall effect was measured in twisted bilayer tungsten diselenide. Okay, so this is the rough band structure of this material. So again, here the interesting part is that you can have this conventional quantum spin Hall effect, and you can have double quantum spin Hall effect, where you have two edge states with one spin and two edge states with the other spin, because the underlying Chern number is 2, not 1. Okay, so there are Hall effect with C equal to 2 rather than 1. Anyways, again, if you look at the resistance as a function of the gate voltage, you get these two bumps, which if you're willing, you can sort of call almost quantization. Okay, so good enough, anyways, right? So again, magnetic field dependence is what you expect, drop of conductance of magnetic field, except again there is some weird saturation at low temperature. Okay, again, very, very sharp suppression. So basically, these are the considerations that I will try to address in what follows. So this has been the review of experiments. Let me start with the review of theory. Okay, so what causes the suppression of the conductance at zero magnetic field? What causes the magnetic field dependence of the conductance? If you look at the literature, the answer is basically crystal clear. So it's either magnetic impurities or puddles or some interactions or elastic backscattering or spontaneous breakdown or nuclear magnetic moments or noise-induced backscattering. So basically, you would summarize this with Tolstoy way. So all quantized conductance are like non-quantized conductance is non-quantized in its own way. Okay? So this is a large list of things. Okay, so again, I'm going to be putting another item on this list. So we'll see whether this is justified or not in a second. Okay, so let me kind of condense all these observations into a puzzle. Okay, and I will disregard the suppression of conductance at zero magnetic field for now. I have nothing to say about that. Okay, but I will be talking about the magnetoconductance. So one sort of thing that jumps at you when you look at this data is that the magnetic field is unreasonably effective at suppressing the conductance. Okay, so what does it mean unreasonably effective? You take magnetic field. I'm going to be generous, half a Tesla. Okay, you convert it to an energy. Okay, you multiply it by Bohr magneton, by G factor, whatever you need to multiply it. Okay, you'll get I told you I'm going to be generous. I should have put 5 Kelvin. Okay, so it's for G equal to 2, one Tesla is 1 Kelvin. Okay, so let's say G is equal to 5 or 10. Okay, nobody reported 100 or 1,000. Okay, so anything reasonable will give you an energy of a few Kelvin. Okay, so basically this means that this magnetic field of this magnitude needs to be comparable to something to kill this conductance. Okay, so it's actually very hard to imagine, what that something can be. You can say, of course, there is a Dirac point on the edge. Magnetic field opens up a gap. So if you put chemical potential right into that gap, of course, it will suppress the conductance by a lot, right? So maybe only thermally excited carriers will conduct, and you will get suppression. But it's actually very hard to do that. Okay, to put chemical potential into that tiny gap, it basically never happens. Okay, and moreover, if you scan gate voltage through the gap, especially on this tungsten telluride, you don't get any special point where it's suppressed much stronger than everywhere else. Okay, so it's just this gap opening is probably not relevant ever. Okay, so then what can happen? So okay, so the edge of these samples are fairly disordered. There are impurities. What does magnetic field do? If your chemical potential runs somewhere here, it will tilt the spins. They were like this, orthogonal. It'll tilt in the same direction, so they're not orthogonal anymore. So backscattering is possible. So perhaps that is the suppression. So the problem is that the typical spin splitting at the Fermi surface, at the Fermi level, is 10 millivolts. Okay, at maybe 10 millivolts. So multiplied by 10, you will get Kelvin. Okay, so that's way larger than this. Okay, so it's a small perturbative effect, quadratic in the magnetic field. You can say, well, look, there is one impurity that barely scatters, but maybe there is a million of them. Fair enough. But then basically what you will see is that if you pursue that line of thought, your conductance will just go down like this. Okay, there will never be any kind of tail of the conductance. Okay, if you try to mimic this sharp drop at small magnetic field. So I don't think basically this scattering on the edge actually works to explain the experiments. And then what are the options? What do we do? So if you want magnetic field to have a strong effect, apart from opening up a gap, which I think is irrelevant, basically, you need to give it a chance. You give it a chance by either letting it produce some large flux. Maybe there is a puddle, some large compressible region. Electron goes in that region. There is a large flux. It loses memory where it came from. Something like that. It's possible. Okay, or you let magnetic field precess something for a long time. Okay, so either big flux or long precession time. So if fluxes are important here, there would have been a large difference between, of course, out of plane and in plane fields. Okay, so this tungsten ditelluride is a fortunate material from that point of view because this edge spin polarization due to low symmetry basically points like this. Okay, this is in plane, out of plane, points like that. Okay, so there is really, from spin point of view, there is not much difference between out of plane and in plane. But from the orbital point of view, there's a large difference. And if you look at these curves, basically there is not much difference between these two orientations of magnetic field. So the orbital physics is probably irrelevant in this case. So it got to be spin physics. If it's spin physics, something has to precess by a lot. And as we just discussed, it cannot precess by a lot on the edge because magnetic field has to work against this spin orbit field. Okay, just cannot precess things. So one naturally is led to the conclusion that the scattering is actually not on the edge, but away from the edge. Okay, somewhere close to the edge. So this is then the model that I'm going to describe in what follows. I will look at a flake. Okay, flake measured by David Cobden's group. Okay, so this flake typically has, it's very large. So there is a part of the edge that is between the source and drain, and there is a complementary piece which is much longer. So it's very resistive. I forget about it. Okay, so I only look at this piece of the edge, and I will essentially consider scattering on this edge on these objects. I will call them mid-gap states, but they can be whatever you want them to be. I will assume that there is some scatter, basically a side coupled to this edge, and I will I will see what happens basically in linear and nonlinear transport in this model. So let me go through this basically qualitatively. Okay, so to explain the mechanisms relevant here, think about the following diagram. So this y direction is the direction into the sample, into the bulk of the sample, and the vertical axis is energy. So somewhere here close to zero, I have my edge states, okay, these counter-propagating states, okay? And then as I go into the bulk of the system, I have for now just one mid-gap state, this one impurity state, which I denote with a bar. The height of this bar is the width of the level, okay? So electrons, as they zoom past this impurity, they tunnel onto this impurity, spend some time there and tunnel back. So the crucial observation here is that by Kramer's theorem, without magnetic field, the levels of this impurity are degenerate. Okay, so magnetic field splits the levels, and that's the singular part of its effect. And classically, you can think about basically precession. You jump onto this impurity, you precess for some time, and then you jump back on the edge. So how long does this precession last? If the level is resonant with the electron, for simplicity, the precession will happen 1 over gamma, 1 over width seconds. You multiply it by the Larmor frequency. This is the precession angle. So if this is of order of 1, so B in appropriate unit is of order of the width of the level. Precession will be by a large angle. So you jump onto the impurity, you precess, you basically forget which edge you came from. Okay, you can go further, like the same spin, or you can go back as a flip spin. Okay, so of course this cannot last forever. Basically, if magnetic field is too large, this classical point of view fails. You basically have two levels that are completely detuned from the electron, and the scattering goes down again. So if you combine these considerations, you basically have a graph. This is a calculated reflection probability. It reaches a maximum when B is equal to gamma, again, in the right units. So Larmor frequency, H bar Larmor frequency is equal to gamma. And then it goes back down, okay? So what's the conclusion here? What's the conclusion? The conclusion is that strong scatterer, you see that there's a resonance in backscatter rather than transmission, like you would have for resonance. So strong scatterers have their widths just right. If it's too small, not much scattering. If it's too large, not much scattering again. So you have to be the sweet spot, to scatter strongly. So what happens when there are many impurities? So of course, the impurity widths, level widths, will go down as you go away from the edge. Okay, of course, it will stay finite because there are other mechanisms of getting lifetime, but the lifetime due to coupling to the edge will go down. So if you look in real space, right, impurities that are too close to the edge are too wide. Okay, impurities that are too far from the edge are too narrow. Okay, so there is this sweet spot. There is a stripe in real space of impurities which are just right. Yeah, they're not too wide, not too narrow. If you look in energy space, this is the same diagram as I described before. If you look in the energy space, again, if you are almost resonant with the electrons, fantastic. The scattering is very strong. But if you get detuned, again, by H bar, omega L, if you are here or here, that is bad. You're not resonant anymore. You're not strongly scattering anymore. So there is a stripe in energy space, okay, of these strong scatterers. So obviously, at the intersection of these two stripes, there are these magic impurities that scatter you like crazy. Okay, so you can immediately estimate the number of such impurities, assuming making some mild assumption about their density of states, and basically suffice it to say that the number of impurities BS is for backscatterers. I didn't notice that actually. Okay, so the number of these strong scatterers, of course, goes linearly with the length of the edge, but also go linearly with the magnitude of magnetic field. Okay, so and that is basically our explanation of this singularity at small magnetic field, this discussed in the conductance at small magnetic field. Okay.
So do you why linearly with the magnitude of field?
So basically, you just have to differentiate things. You'll just see that. But you can tell this comes essentially from the width of this stripe. If you will,
it's Zeeman energy is linear in B. That's what
yeah, that's exactly that. This stripe is linear in B, and this is how many impurities you get. This is as simple as that.
But the other stripe,
it kind of basically can so basically the width of this stripe is of order of B itself, right? And then the rate with which the gamma changes basically goes as 1 over B. So there's this cancellation, and then the only thing that you have left is this width. So it just works out. Okay. So this I meant just as a slide, the FYI slide. So you see what I do, but I'm not gonna do much explanation here. So this linear transport part we just did using the non-interacting Anderson model. So you have the Hamiltonian contains the edge state, contains the impurity. We only included magnetic field on the impurity side because it cannot do much on the edge for small magnetic field at each. And then there is a hybridization between the edge and the impurity. Okay, so this is the curve you get for the reflection, and then basically you can do coherent transport, basic localization on the edge. You can do incoherent transport where when you add impurities, you can actually consider gap opening. I will not go through details, but the key thing is that the angular dependence of magnetoconductance and magnetic field orientation is different in the 3 cases. So this is how you can distinguish basically one from the other. So, basically, let me make one statement. So in those works that I mentioned, and in general, comparison to experiment actually is very rarely made, if at all. So typically people just throw a mechanism at you, put in some numbers, and it kind of can work. Okay, so nobody draws lines from through data. So here we are able to draw lines through data, but one should not be too optimistic about it, because essentially no matter what you think of, we'll be able to draw lines through data. Okay, this is I became disillusioned with fits to experimental data here, because anything fits. These are very simple curves. They have opening at small field and then width at large field. So if you take a particular angle, particular orientation, and look at a G as function of magnetic field, everything will work. Lagrange liquid, sure. Phonons, sure. Everything works. Okay. And that's how I said. I said, I'm such a fantastic theorist. Nobody can explain anything. The first thing I do, it works. Okay. So it turns out that anything works. But the non-trivial thing is to choose a couple of parameters to describe these curves, and then fit all angles. Okay. If you have to change them from angle to angle, this is not good. But if you choose a couple of parameters and everything works, this is sort of okay. Okay. So basically, it turns out that with this point of view that we took, this scattering on the side coupled impurities, you choose a couple of parameters, and then everything falls in place. Okay. You can basically fit all the curves. You can extract the dependence of the slope at small magnetic field on the orientation of magnetic field, and you get sine squared. Basically, the points are experiment, and the line is what you get from this consideration. So overall, you get small b resistance that goes as magnitude of b times sine squared. So b squared sine squared would have been easy. B sine would have been easy, but b sine squared is non-trivial, and that's what it comes out to be. Okay, fine. So this is the linear transport story. So, but this is a standard experiment that everybody else does. So what David did was to go beyond linear response, and this is a work that we're preparing together with people who did experiments, and with 2 students in my group. Gary Korisima is right there. Okay, okay, and then Yu-John Chen is going to be talking about this at the March meeting. So let me tell you what this story is about real quick. So it turns out that if you look at the IV curve for this sample, okay, and you look at fairly large voltages, you see somewhere here, then the IV curve actually depends on the direction of magnetic field. Okay, so basically, for given voltage, current is different for B that way and that way, or if you keep B, current is different for this bias or this bias. Okay, so the transport is non-reciprocal. Okay, okay, so this is absolutely fine. So in general, you can write currents as a function of voltage, with a first couple of terms in the expansion, and you will get the linear conductance, and you will get non-linear term, which goes as v squared. Typically, it's there when inversion is broken, but it's automatically broken on the edge, so it's completely fine. And it turns out that this coefficient, this nonlinear conductance gamma, is allowed to have an odd in B part, because basically it's not forbidden by Onzaga relation. So this has to be an even function of B by Onzaga relations. This doesn't have to be. Okay, so there is an odd in B part, and it turns out that this odd in B part knows about spin texture just like the linear conductance. Okay, so you see that basically if you look at the angle orientation of magnetic field, you have a zero essentially for orientation perpendicular to the edge spin polarization. You have a local minimum along the spin edge spin polarization. You have some a bump in between. So it knows about the whole thing that the linear conductance knows about, and there are a little bit more I'll discuss. So basically, this actually is the first thing that we tried to explain about the experiment before we knew the theory for linear conductance. And the way we approached it was very, very primitive. So the idea is the following, that this is a quantum spin Hall edge. So in order to pass current through it, you need to polarize it. Okay. So this is the edge dispersion. Basically, right movers have spin up, left movers have spin down. If you want to have current, you have to have more right movers than left movers. It's polarized. Okay. So if it's polarized, if electrons are interacting, that means that the electrons feel a mean field, so to speak. Okay, some exchange field, some effective Zeeman field, which act just like external Zeeman field. Okay, so you can actually get or attempt to get the nonlinear conductance by just substituting magnetic field, external magnetic field, in the linear conductance with the sum of magnetic field and current-induced magnetic field. Okay, so obviously this is a nonlinear function of voltage, actually. Okay, so and then the beauty of it is that they had so much data, David and company had so much data on the linear conductance that you can just numerically differentiate it, calculate the gradient in the magnetic field space and calculate the nonlinear piece. Okay, just from the linear one, not knowing anything about the mechanism. Okay, so this is the expression, but if you can differentiate, you can get this expression. Right? And then basically beautiful things happen. So you take a relatively large magnetic field, okay, and then the measured signal looks like this. Measured signal meaning this gamma is a function of a nonlinear conductance as a function of magnetic field orientation. This is the measured one. This is this the one that extracted from the linear conductance. Okay, so they're really not immediately on top of each other, but you see that you reproduce every feature of the measured signal. Okay. So here on these two right panels, there is a breakup into, basically effective variation of magnitude of B because of current and, perpendicular component of B because of current. So they look like this, and the sum looks like what you measure. Great. For large magnetic fields, it works beautifully. You go to small magnetic field and you get garbage, complete garbage. So this is what's measured. Okay. And this is what you get from the linear conductance. Okay. So this point of view that I try to present basically does not work at all at small magnetic fields. So, however, at that point we didn't know, we didn't have a theory of low magnetic field magnetoconductance. But now that we have this point of view based on side-coupled impurities, it suggests that this argument should be basically revised. Okay, so if scattering happens away from the edge, then this current-induced polarization should be calculated away from the edge where the scattering happens. Okay, and then this needs to be rethought. So let's see what happens. Okay, so that's what I just said. So basically, I am using the same kind of diagram that I used before. At the edge, I have this essentially spin polarized metal. Okay, so these spin polarized electrons hop onto the impurity, and their spins precess around the magnetic field on the impurity. Okay, so of course, each individual electron hops on the impurity and precesses the individual, and then you sum up all these signals, and that's your average polarization of that impurity. And here it's actually clear what the difference with the edge, with the scattering on the edge is. Basically, on the edge, wrong direction. Still wrong direction. Was it right direction before? Right here, I assume that the scattering was exactly where the spin polarization was induced, and then this spin polarization direction was pinned by this edge spin orbit coupling. Okay, when you go to this situation, the spin polarization on the scattering site is not pinned by anything. Basically, it comes from these spin polarized guys tunneling here and then precessing on magnetic field. Okay, and then you see that the components along the magnetic field add coherently; they don't precess. And these guys add incoherently, so there is a difference between them that way. Okay, so it's sort of a qualitative clue that this might be relevant. And then we basically consider this problem by adding a Hubbard U on the impurity site. Okay, and we just blindly treat it in Hartree-Fock approximation. Okay, it's just do perturbation theory in U. Okay. So mean field in U, and then you can of course trade this Hubbard coupling for some sort of effective exchange coupling that depends on the density matrix of the electrons on the impurity site, which you can calculate. Okay, and this is what you get. So using this point of view, basically you see that as you consider relatively small magnetic fields, 0.2 Tesla, 0.3 Tesla, what you measure more or less goes through the theoretical curves, or the other way around. Theoretical curves go through what you measure. Okay. Okay. So if you go to higher magnetic fields, there are these deviations, and I think this basically means that at higher magnetic fields, scattering switches to actually this on the edge scattering, usual potential scattering. So you have a different transport mechanism, and you get different nonlinear transport. So this nonlinear transport is kind of smart. Okay. So I have to be done by now. So let me basically tell you the main feature of this results. First of all, it gets the angular dependence of the nonlinear single, right? Okay, the temperature dependence is 1/T. It's actually a bit too fast for what's observed, but then it's at such high voltages that the temperature, the nominal temperature, is probably very different from the actual electronic temperature on the edge. So temperature dependence is very iffy here. The biggest wrinkle on this, peachy picture is that now for these small magnetic fields, the linear transport and nonlinear transport are determined presumably by the same mechanism. So we can assume that if we know everything about linear transport, we can extract this U that is needed to get the right nonlinear and it comes out to be 1 Kelvin. How many times have you seen Hubbard U that is 1 Kelvin? Okay, this is a little bit weird. But maybe it's okay. First of all, it kind of justifies what we did, right? That U should be small, and we did perturbation theory. But how can it be so small? Well, the only answer is that the system has got to be very, very polarizing. So speaking of that, we can go back to these graphs that I showed you before. I should have copied them. Sorry. You see that this WT2 monolayer is thought to host exciton insulator in the ground state. So you see that there is this robust features in the conductance. This is bulk conduction. You see that there's this non-smeared, needs that David likes very much, and basically says that this is a sign of some interaction physics in the ground state. So maybe this is just an effect of this polarizable excitons, floating around or something like that. Okay, but right, U that is equal to 1 Kelvin is strange. Okay, but everything else sort of works. So with that, let me stop because I see Sasha pushing me to do that non-verbally. So I knew that I wouldn't get to conclusion. So there's one conclusion. Things work. That's the main conclusion. All right. Thank you very much.
Yeah, you started off with this 2007 picture and everything's quantum and topological. What's left at this point is there, it seems so fragile, everything scatters into everything else. Why do we care? Honestly, no, I'm not about your work. It's great that you understood it.
Yeah,
is there anything here?
I don't care.
It's great, but I'm saying, is there?
There are a whole lot of experience in this though, right? So basically, in 2019, Molenkamp and company put out another paper where they showed that if you, how did they call it? Gauge train your sample. You just change gate voltage back and forth. Basically, they say their interpretation that you fill some charge traps in your dielectric and the conduction goes up substantially, so they can make it more robust. but are you gonna make?
Quantization or what?
Yeah. The quantization persists in much longer samples. Okay, so whether you're gonna make a dissipationless channel for quantum computers, of course not, because you have to connect channels to the quantum computer. But that's
Is there
the
something that's preserved?
Huh?
It seems like it's so susceptible to scattering. There's no protection. We got sort of spoiled by the quantum Hall effect.
Oh, yeah. This is light years from quantum Hall effect in terms of stability, right? Yeah, that's true.
So I have a comment actually related to your question also.
I didn't know.
There's an experiment after the first Boulder Cup experiment where they take different multi-terminals, 6 terminals, and they actually have much better conductors than the one.
Yeah. So there is a
Much
decade left, right? There are better.
So what length scale is a quantized though?
Well, I mean, you can go and read the paper. It's like
Just tell me.
Yeah, no, it tends
quantization.
tens of microns actually, according to
Well, look at
tens of microns up to 100, I think, 100 something.
But coming,
scale, come on.
You mean you want quantized quantized? No, sorry. No,
There's no
right. No, it's not that quantized. Yes.
there was a comment actually related to it, but my question is, you basically mentioned that, right, if I just have this Dirac node on the edge, I can never, my rotation is never going to be in the gap. And basically, if it was in the gap, I could explain this, right?
Yeah.
Effectively, if I have an impurity band, because you're basically putting an impurity band, or let's say it's not impurity band, but you're putting impurities, let me make it a band. Effectively, you're putting it at the Fermi level. If I have that, then I can just open the gap there, right? Because if I just couple your channel to a double.
You mean some Ledinger liquid type gap or helical liquid gap or actually single particle gap, mobility gap.
Even single particle gap in a magnetic field, you'd open it at the Fermi level if I just couple it like this, right? Because every double degeneracy will open.
You need to have certain coherence through, for this
I
process,
agree,
right?
but there is that, right? Is that similar, basically, what you're saying?
I mean, every reduction in conduction is similar, right? But I'm not sure.
Give you a gap opening, this is open from the.
So I don't think you can interpret it as a gap. So the B dependence kind of looks like a gap, but it's not activated. Right? It's e to the minus b, but it's not activated. So if that's what you mean.
Yes, so I have basically another comment, yes, on the position of the Dirac nodes. So you said that yes, it's highly unlikely there's going to be sitting at the Fermi level, but if you realistically assume that there is some background potential which is changing from place to place, in fact, it's highly likely that at some point it's going to be crossing the Fermi level.
We're working on that. Yes.
So do you have a counter argument?
Basically, the angular dependence on magnetic field will be different from this, and this nonlinear transport will also be different. I have no doubt that it's relevant in some materials, but probably not in this one.
So it was one of those things that have been tried.
No, we're working on them.
Yeah, so the model is very interesting, the scattering from the edge into the impurity levels and both. But let me ask you, does this argument also hold for the surface state of 3D TI?
So for 3D TI, so I think dimensionality matters here. So basically here you jump on the impurity and you either go further or you go back, right? There you jump onto that impurity and you go sideways. Okay, so I don't think it's as important in that situation.
Yeah, I think that there is no localization, but there is no quantization either.
Right, but the question is, does that also give you a very strong resistance?
Right, so I don't think so. Right, I think this one dimensionality of this problem is
perhaps not so. Yeah.
So one more question there.
So Dima, you were focusing on trying to understand the magnetoresistance.
Yes.
And but you also pointed out that the quantization was not overwhelming even at zero magnetic field. Is there anything in the picture you're presenting that can help understanding that?
No. So I would say a reasonable point of view on this is the one by Marco Polini, where they say that, look, this is a correlated material. So if you have a vacancy, it'll have magnetic moments. Okay, and there will be scattering on these magnetic moments. Okay, so which will suppress conductance even at zero temperature. So this doesn't really spoil what I'm talking about, because those magnetic moments they're not spin one half. They have anisotropy. They point this way. So with 0.1 Tesla, you will not do anything to what caused the suppression of the conductance in the first place. So it's on top of that. But you can imagine reasons for suppression in this particular material.
Okay, it's the last one.
So you mentioned this exciton condensate, right?
Yeah.
So I guess this exciton condensation is breaking some symmetry, right?
According to some papers, right? You're talking about the spin spiral.
Yes.
Exciton
condensation has to break a symmetry.
So actually, so this is a whole different can of worms, right? So presumably there is exciton condensation. Nobody has seen associated charge density wave. Okay. So Sid Parnasran has a paper saying that this is actually a spin spiral. Okay, spin spirals generically don't couple to charge. So it's like spin density wave will induce charge variation, but spin spiral won't. So maybe it's but then time reversal is broken. But Gerald Moore has a paper on that. I don't think it quite works like they think it worked. But I don't know.
But the question is, if there is that exciton condensation, then there should be some strong modification to this.
You guys can discuss
Yeah.
this.
But,
All right. Let's thank Dima. Feedback. Hey, good to see you.
It's like
Yeah, I just started. How are you? Good, how are you? Yeah, I know. On the first rule, that's ambition.
По мотивам того, что мы обсуждали, написали with numbers. Experiments they hit so far.
Right, so you're in the middle of.
No, I was just, I sent an email, there's like, you can keep it. But the last time you come, you didn't see what happened last time.
Sure.
But if I close the computer, then the thing will. For some. Yeah, I have read this email
I haven't seen much on it. The only group pursuing
I suppose
for failure system. It's not right.
Maybe it's important
It's
to
not
record.
right. It's still being cited that we do our
You're talking.
Well, no. It's a fundamental question. It's asking if it's so easy to couple.
Okay, I was sure because we spoke about this and I thought that it was all done, but.
What segment?
Yeah.
Well, no, it's easy to break time reversals.
I mean, here, you should be able
There's a million
to.
ways to do that.
Oh, yeah? I just sent an email, I sent him the slides. He said that there's actually. This moves selenite.
I mean, it's.
It's basically what
Okay,
happened
so the
more.
question is how much you can simulate yourself.
So.
Patients can be directed.
We can hear you.
Yeah, this is.
Yeah, I just need to.
Coffee.
Back to the. Sure. That's fine. So it's probably like 30. Well, I will. Yeah. So like 10. Right. It's not like that. That's from the physical separation of the edges. You can't expect it to be. I'm not saying one's better than the
No,
other.
it's 10 to minus 6. not 10 to minus-
Better.
It's 10 to minus 12.
No, but you know what's going on, just busy with things. Yes, and that was the promise of Leonid. And all of them.
Let's just say, okay, so, yeah.
You know, and then I actually.
That's not what we correct, but now.
Yeah, I tried to do this, but it's not right. Channels that you had to be like. It's so easily. Very hard to.
Let's think about this. It's a possibility. I think not to be completely yet, but.
In terms of, then I can dissolve it. These gaps, now basically you change your probability.
I don't think so. One need just to write it down properly. I don't think it's really very, I mean, it just, like, once again, numbers.
I never heard of it.
And then this.
Yeah, exactly. And it's very small also.
So nothing.
There's no. They have a fighting
material system.
You know, so very easy to get again in a fight or chunk. Place here. Then we have a continuous thing here.
The harness suggests. I think it allows much. If you want to like. Type.
Yeah. It's much more interesting. Because this way I can easily get away from your.
Just don't have to get enough time to think about that, but I finally read what I look, but I didn't have such a situation.
Even without on taking a traditional kind of birth.
I know they will, but or try, but that's a roadblock.
Now.
No, I thought before it's rather a little bit data and then.
It's on board, right? So yeah, it's in the development. It will never make scale. I would say, and that's cool. It is looking opposite. I mentioned that.
It's the question how.
Yeah, it's really cool. I'm sorry.
That is, I think, the situation of friends. But it's my understanding. I mean, we know what time it is.
And the fact that, you know, some of the techniques that we've developed for.
And for the future, I think there's just, I think it's Asian process can. 8 or 9. Just.
Yeah, and hold on. Thank you.
That opens the gap in the firmament. Now when you have
So 8 and 9.
and now you've got. So now we're gonna look at the problem of taking this and.
I see.
That's what I think. First of all, activity.
Yeah, so if you consider this problem fully coherent.
Yeah.
Okay, which we did, you will get conductance that goes as minus, magnitude of B times L, whatever is appropriate, right? So I don't know, you can say that there is some gap, right? It's like tunneling, so,
If I just want to add one source, there will be a minus. It will be exactly that quantity situation. It's just really bad, that's quantity.
yeah, right. So you'll have basically this exponential suppressed
Right.
Right, so this just phenomenologically, this doesn't work. If you look at experimental data, it doesn't work. And basically that tells you that the transmission for this thing that you put down so skillfully is not coherent. It's not a bunch of coherent transmissions, right? Where you add Feynman amplitudes. It's really a bunch of resistors. Each ingredient resistor.
Fine, but then can I add, that's just non, so I think it makes your review these are. Then but I think of them, I can make a band of them, then I run this at the front of the bush, and now I. What's it called? Now I just want to add, okay, so here's the key, now I just want to add scalar disturbances. Okay, so because then it means that basically
What do you want to accomplish? So what do you want to accomplish? So,
well, I mean,
what's your goal?
I'm not sure what my goal is, I want us to understand this. Like I said, if I understand this in this.
Maybe you want to ask whether, this single impurity problem can be really considered separate from scalar potential, which always exists, right?
Well, I'm saying that if I look at this, then it's natural. Which is basically.
I agree with that.
It's basically like giving, right, so when your point was. The right point, and if I just don't have any good, then. You're not. But now, if you add impurity then, and you're adding them higher balance, then, I say, oh.
I think this is from French weather, remember this?
Yeah, those things.
Yeah.
Yeah, I have. Now it's making up the other. And what you see the working here. See what I mean?
Yeah.
I guess the doctor is.
It's a narrow. There's very easy.
Ну как это будет, ты сказать, что это здесь? Я не знаю.
And I take the tunnel.
Right.
Ну, я не говорю про такого.
So, if you're moving elastic, you will get the second ideal states of the like you'll have waves, right?
Just some.
And basically, it's a matter of something. So,
So I guess. I mean,
чисто что получается.
They're, since you don't have a translation.
they're not block wave, they can be localized, they are localized. And then that's basically situations like this, right? If you have a function localized. Then you have exact states localizing that. Especially
So now in this problem, so we have continuous relationships in couple. So basically, because it's continuous. So your exact state are not just localized states, they are scattered. So right? You spend some time in this mess, and then you go out that way, right? And I think that is correct. Right.
Эти буквально не бывает, но просто вот прогресс прав. Не прогресс. Гибко, а не прогресс. Если двигается, значит ничего. Просто. Да. Это не кубист.
What's the trivial and it's always lurking behind all this. In the middle, or maybe. And the way
Doesn't get to my mind that Josh here treats me so well and did that thing. I didn't tell you the details, right? So he gave that project to Peter Hart. I met, like, remember the
You told me it was another.
yeah, so he gave it to Peter Hart, and Peter Hart had two Brazilian companies, and they both worked on that project. Remember the Bolsonaro? Thais, she worked on that project. And Vitor Quito is the nicest man I ever met.
Think so, yeah, I'm trying to finish up. Good to see you.
Это правильно сказали. Потом, ну, что
Yeah, just one just have to.
Там есть совсем много, сказать, опять гармонично. Hi, yes, I think we met.
Or like
Cheers. Do you have any thoughts on this most kinetics talk?
old emails, basically everybody.
It sounded like.
It covered some. Jimmy told me before that like.
Yeah.
With them,
Like lots of the
if
people.
you just email, they don't know you.
I don't know, it seems
Like,
like
emails, they're gonna ignore it.
That way.
This is weird.
Yeah.
We made
Really, at least I don't know. I was
We
most
actually
curious
made a,
about like how it dealt
meet
with
even the experimental data. He worked on the projects. Like I rolled the project, they wrote in the recommendation letter. It was nice. Which is weird. This is like a crazy situation.
I didn't get much out of it.
What I realized at this point, this is worse for Daniel than for me. I'm nobody, right? Now, like I work with the file, and before I work with the SUT, so it's better for Daniel.
Well, that happens to Daniel a lot, right?
Yeah. The philosophy seems to be the same.
You told me.
Yeah,
Almost the same thing happens.
Oh, really?
Peter up a month.
Okay, wow.
This idea.
Like they're actually friends, right? But then.
Yeah, he told me with Peter is different because but I don't really understand. He says that, you know, they seem politics or something that Peter's not representing. Do not open products. Set a very specific.
Yeah, but like that seems like.
This is not what I said, this is my interpretation.
Sure. I'm just, I mean, it kind of seems like more suspect, right?
Yeah.
Or we can talk about this more like. Because you've seen those papers, we can get into their stage, right? But it's like.
Yeah.
5 authors, most do anything, right? Maybe find some.
I'm gonna ask. I agree. I don't understand.
Like it would have been cheap
Mhm.
for him to be part of that, one of those projects. But he wasn't.
Yep. No.
I don't know, maybe there's something else that's going on in the background.
Yeah. At this point, I actually leave that.
More later though.
Mhm.
It's like they told us before.
You probably got some of that stuff for us.
Probably. I can wait for it.
Bench. I think
I dropped 4 out there. I don't know who is yours or not, but I had to sign it.
okay,
So maybe that's yours. Probably. I just realized it was. Thanks. No problem.
Oh, right, so you're saying, yes, not separated arbitrarily.
No.
You can separate, but this, yeah.
Perfect. No, okay. These are my favorites. Thank you.
That's
welcome to.
Sounds really weird for me to see one of my
Yeah,
students here. I see one of my students. Still in undergrad.
That's like teachers.
All right,
So the more regular.
Okay, so let's start our final session of the day. The first speaker in the session is Magnetotransport from Rice. Short noise. Straight.
Test. Okay, all right, it's working. So hey, thanks to the organizers for inviting me. And so actually, when I first arrived today, I'm sorry I missed yesterday's meeting. I had to teach on Thursday, and I had a conversation with a few people, and apparently there was a straw poll of who's actually going to March meeting and who isn't. And maybe a fair number of us are not actually going to March meeting. I'm actually going. And so I thought, for some of you who actually are going to March meeting, let me just advertise two talks. I didn't put together a huge number of slides for my own talk here. So let me just say a couple of brief things. So my former student and current postdoc Xinghai Zhang, who's somewhere back there, has a talk, I guess, on Tuesday afternoon, entering a field, a very crowded field where we haven't done anything until now, which is twisted bilayer graphene. But one of the things that has been a question, I've kind of watched from the sidelines twisted bilayer graphene, and there was this debate about whether it's topological, is it not topological, is it fragile topological? But I looked at the Bistritzer-McDonald Hamiltonian, which it took me a long time to understand, but I immediately said, hey, that Dirac Hamiltonian is topological, because it looks like the surface state of a certain type of topological superconductor. And we've spent a lot of time in my group studying surface states of topological superconductors and what disorder does to them and what types of weird criticality you can get. So we decided that, hey, although Bistritzer-McDonald elegantly evades quasi-periodicity, we can put quasi-periodicity back in these moire materials, either from the boron nitrate substrate, or now there's twisted trilayer, which is some kind of quasi-crystal. So we thought, hey, let's put two periodic potentials into Bistritzer-McDonald and see what comes out. And that's what Xinghai will talk about. And long story short, we see connections to the topological superconductor surface state physics that, again, my group spent way too much time studying. Now, I myself am giving a different talk on Wednesday, which is actually about topological superconductor surface states. And so I'll just advertise that this was work with Alex Altman, Pete Brower, Johannes Deplinger, Mateo Morena Gonzalez, and Luca Trifanovic. And basically what happened here is Pete and Luca rescued Alex and I from years of hell, where we were trying to understand analytically how to think about these critical surface states, which we found in numerics, starting with some work by Saeed Garashi, who I think is also here somewhere. He's over there. And we finally understood it, and I was never so happy to be wrong about something, because we understood that this robust criticality that we had seen in topological materials is actually not robust. We understand exactly how to destroy it, but it also explains the criticality that we had previously seen in numerics. And so at the end of this talk, I'll show you a refined version of the topological classification table. And it turns out that 4 of the 5 topological classes in 3D are not really topological in the way that we usually think. But I'm not talking about any of this today. That's just if you're actually going to March meetings. So what am I talking about today? Well, the question I want to ask is a broad question, but of course it's going to be informed by some particular theory that I can calculate stuff with. And the question is, when is quantum hydrodynamics quantum hydrodynamics? So you have to put quantum with a capital Q in any talk you give now in order to get money from funding agencies. So this is actually work that was done mainly by my former student, TC Wu, who has seen the light and gone off to finance instead. The first work was done in collaboration with Yancheng Liao, who's now a professor at KTH. The second work involving superconductivity was done in collaboration with Patrick Lee. And so, okay, let me give a very short introduction to hydrodynamics, the usual story of hydrodynamics. This is basically coming straight out of Alex Kamenev's book. So, how do we think about hydrodynamics with respect to quantum systems, right? Well, I mean, in principle, I could take any quantum system I want and write a series of Dyson equations. And these Dyson equations for what plays the role of the distribution function are exact. And if I can compute these self-energies, these are all bilocal matrix fields, then in principle, I could have a quantum theory of hydrodynamics. But in practice, this is very hard. And what we almost always do is throw out essentially all the quantum physics and reduce it to some kind of semi-classical kinetic equation. So in this case, this would be a diffusive semi-classical kinetic equation with some collision integral on the right-hand side that encodes, say, real inelastic processes from electron-electron scattering, right? And then what's hydrodynamics? Well, hydrodynamics is just integrating this over frequency and deriving an effective diffusive equation or Navier-Stokes equation where all you're doing is tracking the flows of conserved quantities. And so although hydrodynamics can produce very intricate structures like the flow field across a lobster, which somebody decided to compute on the internet, there's no quantum mechanics in either of these, right? So what do I mean by quantum hydrodynamics? Well, there's one example that we all know and understand, which I would say is a fully quantum mechanical theory of hydrodynamics. And that's bosonization in 1D, right? So in one dimension, I can have fermions on the line moving with some effective Fermi velocity, and I have some generic short-range, say, density-density interactions. And so we all know what we're supposed to do. You bosonize the system in terms of some effective free boson theory. But although this is a free boson theory, I want to emphasize it's fully quantum mechanical and it's hydrodynamic, meaning that the natural degrees of freedom in the bosonic theory are the currents themselves. They satisfy a current algebra. You can consider any state in Fock space with any background charge and put particle hole excitations on top of it. So it's a very simple theory, but it is fully quantum mechanical. Now, why would you want to use this effective field theory to describe this interacting fermion system? Well, it's not even an effective field theory, it's so exact mapping in some sense here. Well, of course, the answer is that this guy is a strongly correlated electron liquid, a Luttinger liquid, right? So your bare fermion acquires an anomalous dimension, and that means the fermions, say at finite temperature, decay rapidly due to interactions. And this, you get all these funny power laws and observables, like if you look at the fermion occupation, the fermion anomalous dimension shows up here. So the individual quasi-particles are ill-defined. They're not good long-lived degrees of freedom. Therefore, you want to use the quantum hydrodynamic theory to make predictions.
But another point of view is that the theta fields, they are bosonic quasi-particles, which are collisionless.
That's right. That's right.
Of course. Why would you call that hydrodynamics? I know people
exactly,
do.
Right. So it's right. It's not really hydrodynamics. It's kind of a trivial hydrodynamics. But all I'm saying is that it's hydrodynamic variables. It's density and current, which are encoded as free bosons. Obviously, this is a too trivial theory.
Well, I mean, I would suggest, okay, it's a really greater expansion. What makes things even worse is that if you take next derivative, it actually leads to singular perturbations.
Right. No,
right?
It's certainly if you look at spectral functions, right. So I don't want to.
So it's not dynamics at all. I'm saying.
Sorry, it's not.
It's free particles, but not better dynamics.
Okay. Point taken. I would say it's hydrodynamics only in the sense of. I just mean you're calculating correlation functions of density or current, right? You're calculating, it's formulated in terms of those variables, right? Which usually we don't have a theory formulated directly in terms of those variables. We have a particle theory. That's all I mean. And the other thing you do with bosonization is that you can, which is an unusual thing to do. If you think about a theory that's only encoding the flow of conserved quantities, is you can actually use it to calculate whole phase diagrams of systems, right? And so this is the standard textbook thing of you calculate the CDW instability or the instability to the Luther-Emery liquid or whatever, right? But of course, there are many caveats here. It works in 1+1 dimensions only. It's a trivial theory. It's a free theory. And it's because it's a free theory, it's hard to get interesting transport effects. So it's hard to take, say, that anomalous dimension for the fermion and turn it into some interesting transport dynamics. You all know that if I attach ideal leads to a Luttinger liquid, I measure E²/h, irrespective of the Luttinger parameter. There are ways to do it. So I'll just mention some paper we had in PRL back in 2019, where we thought about quenching together a bunch of Luttinger liquids, and you could get interesting waves that move in different directions, depending on whether the system is fractionalized or not. But in general, this is a very exotic thing. You have to work very hard, right? Okay, so what are we actually doing? So our interest was in trying to build up a quantum hydrodynamics for a strongly interacting fermion system. So these are the ingredients to the theory. These are, if you do strongly correlated physics for a living, this is all very familiar. Our particular inspiration was actually from this paper from Pavel Nosov, who's somewhere in the audience, Igor Burmistrov and Sri Raghu, where they were trying to do something very similar. In fact, our starting point is basically the same. So we have n-flavored electrons and living on a Fermi surface in 2 dimensions. These n-flavored electrons interact with SUN matrix bosons. And why SUN matrix bosons instead of the usual large N bosons? Well, there was an argument that at least in the clean limit, this has a better defined large N limit. That's not going to be important for us, so I'm not going to emphasize it. They're Yukawa coupled with some coupling G. But also the bosons themselves can have interactions amongst themselves. That's going to be important just to fine tune ourselves so that we're above a 0 temperature quantum critical point. And then finally, the only disorder I'm going to allow in the system is just regular potential disorder. Okay, so we're not going to be doing SYK type disorder here. And so that's a key difference from the type of stuff that Avishkar and Subir and company have done, where they fully break the SUN symmetry. So I'm actually preserving it, and that's going to be important for some quantities that we look at. Okay, so what do we do with this? Well, the first step is essentially standard. It's kind of following SYK logic. So we used the G, sigma, D, pi, or you can just sum diagrams way of getting a large N saddle point where you're doing simultaneous saddle points for the fermions, for the bosons, but you're also smearing everything by disorder. And that's important. The smearing by disorder means you're not going to get the usual non-Fermi liquid physics that you get in 2D with the omega to the 2/3 self-energy and blah, blah, blah. So I don't know, Subir may have presented all of this already on yesterday. But what you get is a marginal Fermi liquid like self-energy, plus a constant scattering rate, of course, because we've got impurity scattering. And yeah, it just comes from summing these diagrams. There's a bunch of parameters here. This coupling is effectively dimensionless. This G bar squared is the ratio of the Yukawa coupling to the elastic scattering rate. And then for the bosons, you get what is a very generic form for the boson propagator at this saddle point level. It's just a quantum relaxational boson. So instead of k squared minus omega squared, it's diffusion now. Alpha is some inverse diffusion constant. But also we're at finite temperature. We're going to only work at finite temperature. We're not going to talk about 0 temperature properties at all. And so I have a thermal mass. And the thermal mass gets various contributions, but we fine tune, say, the boson-boson interactions so that if we were to go down to 0 temperature and not go into some ordered state, the thermal mass would vanish exactly at 0 temperature.
And
yeah.
Are you doing all calculations in 0 frequencies, or you are doing them with Subara and
We are doing everything in Keldysh.
Okay.
So long story short, so those saddle point equations, they're identical to what Subir and Avishkar derived in their work. But we were actually, as I said, inspired by a paper of Pavel. And so we wanted to try to build a so-called nonlinear sigma model, which is an effective field theory to describe transport in this strongly coupled interacting system. And I guess the question that was driving us is the idea that if you have Planckian dissipation of individual quasiparticles, right? Individual quasiparticles don't live long because of this marginal Fermi liquid self-energy. Is the resulting hydrodynamics of the density of the charge purely classical? Or are there still interference effects that can affect quantities of interest? That was the question we wanted to answer. So I wasn't sure how much technical stuff to put in this talk, so I didn't put very much technical stuff. I'm going to mainly focus on the physics. But there's a standard way of deriving such an effective theory by averaging over disorder, decoupling with a certain matrix field, which is appearing here, this Q matrix. There's different ways of dealing with disordered systems. In our case, we just use Keldysh, and so this is a bilocal matrix in frequency. If you're using replicas, it would also have replica indices. And this part of the action is actually the standard type of nonlinear sigma model that is used to describe single particle Anderson localization, except brought into this dynamical context with one additional feature, which to us is we sort of think of this is like our Luttinger parameter. This is the way we're deforming the theory away from the free limit. This fermion self-energy works its way into the frequency term. Okay, so that's going to change our diffusion modes in this effective theory of transport. So if we look at the diffusion modes here, we now get an anomalous diffuson propagator. So this is in the particle hole channel technically.
The dissipation sigma is, I
So I have real and imaginary parts, and they're both there actually. So there's a lifetime, and there's also the log part, which encodes the vanishing of the quasi-particle weight.
But are you keeping the scalar field alive or what?
Yeah, so we retain, essentially, no, we treat the scalar fields essentially at the saddle point level. So we keep that propagator, but we don't consider additional quantum corrections to the scalar field.
So there is no weak localization effects.
So there's no weak localization, but there are still interference effects.
There are no weak localization.
Well, weak localization would be strongly suppressed by the marginal Fermi self-energy as an additional dephasing rate.
Right, so tau phi is what scale the stem linear.
Yeah,
temperature.
exactly. But of course, it does that anyway. Even it's in 2 dimensions, it scales like temperature as well, but with a proof factor.
Right, so
Yeah, it's a coefficient. Yes.
so in which sense quantum is quantum?
Well, you will see. So one thing is that, if you just think about the system semi-classically, so I have these weird diffusion propagators, and if you go and you plug these into the Kubo formula, naively, this is going to translate the marginal Fermi liquid lifetime into a transport lifetime, and you say, oh, great, linear T resistivity. This is what the marginal Fermi liquid people were, Chandra Varma and company were targeting way back when, right? But no, it doesn't work.
Sorry to interrupt.
Yeah.
But is the residual term in electronic self-energy the largest? Or marginal part is larger than residual?
Sorry. So this term, what are you asking?
When you present the expression for the self-energy,
Yeah.
there was a residual term. I got it.
Right.
So which one is the largest in your?
Well, so good. So our theory is an effective diffusive theory. So that means we're only allowed to look on frequencies and momenta that go up to gamma EL. Right, so we can never go beyond gamma EL because that would cross us over into the ballistic limit, which gets super complicated.
Basically means there is a linear T term, but there is a huge constant.
Well, it's worse than that. It's worse than that. So actually, there would be a linear T term, but that's if you only calculate this diagram. So here I'm calculating the density correlation function. But the problem is, if you calculate the density correlation function, you have this weird anomalous diffusion. You quickly realize you're not going to conserve charge. You're going to violate the Ward identity. So actually, in our sigma model, I didn't write it, but there's another term. So when you carefully derive the sigma model, you find that in addition to the interactions mediated by these SUN bosons, there's a density term, and the density term encodes exactly the vertex corrections coming from the boson. And so at the semi-classical level, you have to sum those two. And Subir also found this. And when you do this, unfortunately, the linear T resistivity goes away completely. So you would have marginal Fermi liquid phenomenology at the level of 1 particle observables smeared by disorder, but you would not have linear T resistivity here. It just cancels out completely. We satisfy Ward, but we don't have a strange metal. Okay. So so far, everything here is basically identical to what Avishkar and Subir and company found. But then we decided to go in a different direction. So we built the sigma model, and the sigma model is designed to calculate quantum interference corrections to transport. One of them would be weak localization, but we expect weak localization to be thrown out with the bathwater because of this fast dephasing due to the marginal Fermi liquid self-energy. However, there are other corrections, like Altshuler-Aronoff corrections, which go in the particle hole channel. They're mediated by interactions. And in a weakly interacting system, they have a very simple interpretation. So the interpretation is, if I put impurities down, in my two-dimensional material, then I get Friedel oscillations around each of the impurities. And then if I'm an electron now moving through this landscape in the presence of interactions, I get virtual resonant scattering as I take my wave number to the Fermi energy off of these individual impurities. And so that's an additional correction to transport, which gives you temperature dependence. The temperature is the natural infrared cutoff scale. And normally it gives this in 2 dimensions, it would give this logarithmic temperature correctance. This is why when people talk about weak localization, they usually take it in experiment to be synonymous with magnetoresistance, because temperature dependence will also have ultralight Aharonov corrections. And it's hard to disentangle them because they're both logs.
This picture doesn't seem to have any diffusion in it. I'm confused.
Well, okay, this is a short range. This is the ballistic limit of the process. Yeah. So that's the interpretation. That's the interpretation of the ballistic limit as from the Igor's paper. You don't see that at the level of the signal model calculation.
It comes from 1D, right? So basically, if you take impurity in 1D system, in 1D Fermi liquid, there is Friedel oscillation, there is scattering of Friedel oscillation.
Yes.
And it's logarithmic.
Right.
Okay.
Right.
And basically, this is kind of 2D rendition of the same thing, which is also by paper with Ziegler on ballistic, and then you can. Basically, the thing is that in the original wonderful papers, I mean, there was some arbitrarily upper cutoff, which was given by diffusion time, and actually the correct cutoff even is incorrect. It is different because
because
you have to go to ballistic to get the right cutoff.
Right. Okay.
But it's all understandable scattering of one impurity and the Friedel oscillation that it creates.
Sure. So my only point here is we built this thing, and in the signal model, this comes at the level of a one-loop quantum correction, so we can calculate it. And you derive the formula. We check, first of all, that the ward identity is satisfied. So we're still conserving charge at the level of quantum correction. So the theory seems like it's making sense as a transport theory. And we get basically the standard expression for the Altshuler type Aharonov correction, except this is now our dynamically screened boson, and this is our anomalous diffusion propagator.
And lambda is interaction, but
lambda here is actually the resistance. It's the inverse resistance. So these are all quantum corrections. So they're all down by powers of whatever the conductance.
Yeah, but again, in our material, this is squared. It looks like interaction doesn't enter, but actually it's unitary limit of interaction, right? So because the
this is Coulomb. This is the Coulomb result.
So where's
right? So here G squared is the interaction for the boson. Lambda is the inverse conductance.
So you somehow you put the screen interaction right into the theory.
So actually, well, there's 2 limits. So there's also screening.
So in the screening limit, you get the linear in T. In the ballistic screening.
So we never go to the ballistic limit here. I don't know how to do that because then I have a non-Fermi liquid with this omega to the 2/3, and things get very complicated, right? So we only stay in the diffusive limit here. So what we do is we just calculate in the diffusive limit, but there's actually 2 regimes even in the diffusive limit, depending on whether you're dominated by the thermal mass of the bosons or you're dominated by dynamical screening. So let's take the latter case first. So at very low temperature, you're dominated by dynamical screening, you have full screening, and you get a log squared dependence. And sorry, I didn't write the prefactor, but it's the usual thing, the G squared drops out.
Yeah, okay.
So at very low temperature, that happens. However, at intermediate temperatures, it's funny, simply because the Altshuler Aharonov corrections, these virtual scatterings, are mediated by these bosons. The boson range is the thermal mass. So you get something that goes like 1/T. And so, okay, very naively, at least at a large N limit, if I were to extrapolate this to large T, it looks like it could give me linear T resistivity. Now, okay.
The correction goes as 1/T.
The correction goes as 1/T, yeah.
And if you're right at the critical point, aren't you always in that regime?
Well, it's neglecting the dynamical screening. So when you take into account the dynamical screening, it washes it out.
So this is how does it depend on exactly where you are relative to the quantum critical point?
Okay, so I'm always sitting right on top of the quantum critical point, and I'm just coming down in temperature, but there's a temperature scale which I write, well, it's basically like this. So there's a temperature scale that goes like 1/N times the Yukawa coupling, below which the dynamical screening of the boson line by the fermions becomes important. And when you take that into account, it slows this correction way down to.
Boson mass is no longer going linearly in temperature.
The boson mass is still there. No, the boson mass is still there. I'm just saying that this process becomes more important. It's still there. There's a complicated crossover.
This is the coupling between the boson and the fermions becomes weaker. Is that what?
It's just like Landau damping of the boson line. It's dynamical screening of the boson line.
In terms of your formula, which term is it that suppresses this 1/T effect?
Okay.
Previous formula.
In
that.
Yeah, it's coming from this full line. It's just that
that's the boson propagator, right?
It's not the bare boson propagator. So that's the thing. So the bare boson propagator was frozen. That's a component of the sigma model. But the sigma model itself dresses it with particle hole pairs. And that gives rise to dynamical screening. So even though the boson line itself was frozen, there's additional screening that comes from particle hole pairs. And that's what I'm saying, is that below a certain temperature.
Landau damping changes.
It changes it, yeah, exactly. It changes it.
And it's a 1/temperature correction in the.
It's a 1/temperature correction, yeah, at high temperature, but then it will get slowed way down. Right.
Okay.
So superficially, this seems like a way to get linear T resistivity. It's amusing. Why does it happen? Well, because it's an anti-localizing Altshuler-Aharonov correction, because these boson-boson interactions are attractive rather than repulsive. But would you ever really see it? Well, it's controlled by N. And also this is a very strong scaling. So you might expect that the system wants to do something else. So let's switch gears and talk about disordered superconductivity. Right, so way back in 1960, Phil Anderson said that the way we should think about disorder in superconductors, which by the way is important because most low temperature superconductors are in the so-called dirty limit. It means although they're good metals in the normal state, they're actually, the delta that you get is actually much smaller than 1/the elastic scattering rate. So to really think about ordinary low temperature metallic superconductors, you have to take into account disorder. But Phil Anderson said, well, you should imagine pairing exact eigenstates in the presence of disorder. And as long as there aren't magnetic impurities, everything should go through. And the technical calculation you do is you draw the pairing susceptibility dressed by disorder lines. And what you find is that the transition temperature is given by BCS with no disorder modification. Fine. But then 22 years later, Meikawa and Fukuyama said, well, what about Anderson localization? Does this do anything? And so what they did is they calculated some corrections to the pairing susceptibility that involved disorder lines, but one other ingredient, the Coulomb interaction. So this red line is the dynamically screened Coulomb interaction, and you have to draw all these different diagrams and dress it in different ways. And long story short, what they predicted was actually a weak suppression of the transition temperature. And you can re-derive this result from the sigma model. Finkelstein did it, others did it. It's not totally obvious what's going on with this. It's kind of a complicated formal calculation.
What is lambda?
What is lambda? Lambda is the ultraviolet cutoff, so the elastic scattering rate, basically. So this is a formal, complicated calculation. It's not easy to understand what's going on. But there was a different line of work that occurred around 2010 that really clarified things. And it was a completely different thought idea. So this was, I guess the first paper was 2007. So Misha Feigelman and company were thinking about the following idea. Imagine I have a short-range interacting system, say just fermions with short-range attractive interactions, and I tune myself near an Anderson metal insulator transition. What does that do to pairing? And they had a counterintuitive answer. The counterintuitive answer was that it should raise the transition temperature. Why? Well, there's an aspect of Anderson localization physics that if you don't study this for a living, you might not know about. That's called Chalker scaling. So what I've plotted here are 4 different wave functions in 4 different colors near a 2D metal insulator transition. So if you look at a particular wave function like this green one, you see it consists of sort of clusters of rare peaks. It's actually self-similar. It's fractal on all scales. But you see something else. You see that peaks of different wave functions tend to overlap strongly. This is actually the reason why you have a scaling theory of localization. If the peaks moved randomly as you scan the energy, then you wouldn't have smooth scaling as a function of energy. So this is completely different from the Anderson insulator, where states that are nearby in energy are localized in completely different places. Okay, so near an Anderson metal insulator transition, these wave functions nest like Russian dolls. And so what these guys did was a very simple thought experiment. They said, let's calculate matrix elements between these states just using fractal dimensions that we pull out of numerical simulations of the 3D Anderson transition and calculate TC. And a very sort of optimistic calculation where you do nothing else, you predict that instead of an essential singularity, you would get the coupling to some power where this tau2 is a fractal dimension of these wave functions, which is less than d, so some positive exponent. Now, in reality, this would be cut off by ultraviolet effects, and also this is really a story about the enhancement of the amplitude of a superconductor. You also have to worry about the stiffness, and the stiffness is monotonically decreasing as you make the system disordered. Okay, so what does that have to do with us? Well, one small point. These are actually the same mechanism, and I'm running out of time, so I don't have time to explain this. But the point is that this result that Feigelman and company got, you can also get from the sigma model by drawing these diagrams. And what it turns out is that the BCS interaction is not an eigenoperator of the disorder. It mixes with other interactions. And so what it mixes with is, say, a short-range density-density interaction, or in our case, it's going to be our SUN boson. And if the interaction is short-ranged, then there's only one relevant direction, and you would actually get this enhancement. Coulomb is different because Coulomb has a coupling which is 1 in some sense because the system is incompressible. That's why they got the opposite answer. That's why they got a suppression of TC. So what do? We go and we calculate the same diagrams. So with our sigma model, we calculate the semi-classical diagrams. And now in this case, because of the marginal Fermi liquid self-energy, you get the result that at least I would have expected, which is that TC gets completely squashed, right? So instead of an exponential, I get an exponential of an exponential, where this is the Yukawa coupling, this is the bare BCS coupling, which is just a phenomenological constant for us, okay? So this kind of makes sense. If I have Planckian dissipation and I'm trying to pair these particles together, the system doesn't want to do it. But that's not all. We can go on and calculate these diagrams. So we can calculate the quantum correction to the pairing susceptibility. And now we've done the calculation both above and below the Landau damping, so taking into account the dynamical screening. And in both cases, you get a power law contribution in temperature. So if I put this together, this thing is log of log. It's basically a constant. I can kind of group it with the bare coupling. And then the entire prediction for TC would actually come from the quantum correction. Now, you shouldn't take my prediction for TC seriously any more than you should take any other theorist's prediction for TC seriously. Theorists don't have a good track record with predicting TC in superconductors, but it's a potential mechanism. And it's a mechanism.
How do, I mean, I'm sorry.
Sure.
I'm familiar some of this is my paper, but so what's TC? I mean, how do you define TC?
So just the pole in the pairing susceptibility.
Averaged over everything.
Yes. Yes.
Okay.
Yeah.
So it's
but I mean, so
it's a measurable quantity, right? So
it's a measurable, yeah, of course.
Of
course. But so the only thing I'll say is that, like in the weak coupling case that we understand, where you can look at this multifractal enhancement, we've done this. Actually, Shanghai has done this with Aubry-Andre and parallel random banded matrix models. You can get close to the Anderson transition and still have a well-defined average of delta everywhere. Delta itself is not going into this granular regime where it's really strongly fluctuating. So that's, if this were to work, that's what I would have. Okay, and so I'm probably, okay, I'm almost out of time. So we decided to do one last thing with this theory, just because my colleague at Rice, Doug Nadelson, has been doing shot noise measurements on heavy fermions. I know almost nothing about heavy fermions. And so the calculation we did is for this 2D dirty marginal Fermi liquid. It may or may not have anything to do with the experiment. But what they found in the experiment, so they go and they measure this heavy fermion compound. And what they find is that the shot noise, or just the total excess noise, is much quieter than what you would expect for a diffusive metal. So for a diffusive metal, you should have a Fano factor of 1/3. There's a result due to Negev, which is a semi-classical hydrodynamic result, which says that if you have a strongly interacting fluid, then the interactions in the presence of the large bias create a very inhomogeneous temperature profile across the sample. And then you're supposed to get this √3/4 Fano factor. I don't know if this has ever been observed experimentally, but instead they see something much quieter. And something kind of amusing, I think this was Jan Zanen's influence in the appendix to their paper in the supplemental material. Doug fit their data to this so-called Hawking formula. So this is from a paper from Sonner and Green, inspired by ADS-CFT. I don't understand it. But essentially it says there's an effective electron temperature, and they give this crossover formula. And it actually works reasonably well. Take it or leave it.
Simply to say that's a theory of the boson superfluid insulator.
No, right, exactly. It's the wrong theory, but
yeah, but that's what the theory was for.
Right. So, okay, we can do a similar calculation, but now it's not quantum anymore. This is semi-classical. So we just look at the saddle point of this theory, which gives us a kinetic equation. And it's a diffusive kinetic equation. The marginal Fermi liquid self-energy is now out of equilibrium. It gives us a collision integral. And okay, in general, if you want to actually solve this, you have to find the distribution function for the fermions, find the distribution function for the bosons. That's hard. But we're going to assume, for the physics to be interesting, the device has to be much longer than the electron boson scattering length. So therefore, we're going to assume local equilibrium. And what we find is that if we take both to be in local equilibrium with the same temperature, we get back this √3/4 stuff. No evidence of the marginal Fermi liquid, nothing new or interesting. So if instead we assume that the bosons themselves stay in equilibrium, maybe there's strong quantum critical fluctuations of the bosons off of each other, then we can get something different. And we can actually get a shot noise prediction, which is very similar. I mean, you could call it holographic, but it's basically the same as this Negev 1995 paper, which is just electron phonon scattering. The generic form we get is like this. So it's always d times the electric field squared plus temperature to some power, and the power you get here is just determined by the dimension of this coefficient. Because we have a dimensionless Yukawa coupling, we get a dimensionless coefficient here.
Actually, I'm sorry to interrupt you, but I mean, it's not electron. I mean, in Nagaev, it's electron rather than electron phonon. Electron phonon, electrons would lose energy.
Well, I mean, yeah. So you are losing energy.
But Nagaev, but 1 second. If Nagaev is when you don't lose energy, and then indeed.
No, there's two Nagayevs. There's the √3/4 Nagaev,
Yes.
which gives you the parabolic temperature profile. Yes. But there's also the electron phonon Nagaev where you lose energy. This is analogous to that because I'm keeping the bosons in equilibrium.
Exactly. Yeah. So you can trade your bosons for
yes.
phonons and everything.
Yeah, it's. I'm not saying this is something deep. It's just something we can do with the theory. Okay. Yeah, and okay, so you get a strongly suppressed Fano factor. The one amusing point is that you can ask, well, does the marginal Fermi liquid stuff do anything? And there was some argument in this shot noise paper that somehow having ill-defined quasi-particles would make the system quieter. What's amusing is that we get a tiny correction which is in the wrong direction. It's actually making it a little bit noisier. It's a very small effect. The main effect is just dissipation coming from these bosons. But okay, so now I'm done. So we derived this marginal Fermi liquid modified sigma model. And it seems like at least some interference effects, or at least I would call them interference effects in the weakly interacting case, survive. And so I think the most interesting question is, can quantum interference survive despite strong dissipation of individual quasi-particles? And if so, then what is it that's actually interfering? I don't actually know. That's it.
Two very simple questions.
Sure.
First, when you started, you put linear in T term in a bosonic propagator.
Right.
You did it by hand?
Yeah, it's a thermal mass generated. I mean, you can get it from the saddle point of the boson-boson interactions, but yes, it's essentially by hand.
My point here is that it's completely unrelated to low energy theory. So it comes with its own overall factor, which can be small or large.
That's right.
And question is this: when you said that there is a cancellation of would be linear in T term because of what I did here.
Yeah.
Just curious, what is left over?
Yeah, so that's a good question. So within the diffusive theory, we don't see anything. But I think I know in your guys' work, I think you get a T-squared correction, if I remember.
Shot noise?
No, not for shot noise, just for the residual temperature dependence of the resistivity without the random spatial Yukawa. There's some left over. It's not linear T, but there's some higher order. Yeah. So yeah. Yes.
Can hydrodynamic be quantum?
I don't know. I'm asking you.
It's your talk.
Can I make a quick comment? So I gave a talk on Monday, which and many people know that I'm giving a talk sorry, I gave a talk on Friday. I'm giving a talk on Monday at the March meeting if you want to come. But I agree with you that it's very important to look at the feedback onto the boson propagator, and that's kind of what we've done in our recent work. So in a very different way.
So let's thank that. Let's think with my and Michael tells us what hanging up about the machine.
Great. Well, thank you. And I want to extend the thanks to the organizers for inviting me. I think this is actually the first time I've had a chance to give a talk at Minnesota. So it's a good opportunity, and hopefully I'll be able to explain some of the work that we've been doing over the last few years. Also, there's another first. I checked the schedule, and it's 4 o'clock on the second day of the conference. I think I'm the first experimental speaker. So there'll be some more tomorrow. All right. So I'm going to describe to you some of our work on trying to expose the properties of anions. And I'll be talking about fractional quantum Hall systems in gallium arsenide, but I hope over the course of the talk you'll understand that there's a lot of material systems right now that have the potential for hosting anions, and so it's a very exciting time experimentally. Despite my comments to an earlier speaker, I'm very optimistic, and there's a lot of interesting systems that are potentially fractionalized, and so that's an important point. So, the history of fractional statistics in low-dimensional systems is long. I think it started roughly in the late 70s with the work of some mathematical physicists, Leonid and Mirhan. There's been many contributions to this in the early days. Of course, Frank Wilczek played an important role. And here I'm talking about the early developments of abelian anions. And later on, the discussion of the importance of non-abelian anions to the fractional quantum Hall effect began, I believe, with the work of Moore and Reed in the early 90s. So if I missed anyone, I apologize. This is just maybe a partial list. But this notion that we all know that the fundamental particles in 3+1 dimensions are fermions or bosons, and that they're, whether they're fermions or bosons, there's the spin statistics theorem. And so we know that that's the case, that we're going to have bosons or fermions in 3 dimensions. But the idea that the statistics would be different in low-dimensional systems, specifically 2 dimensions, really began with the work of these theorists. So I like to start, just when I'm giving a talk, from Frank's paper from '82, where he was considering the quantum mechanics of fractional spin particles. And it's actually prescient because he was considering the toy model in which the charged particle is attached to a vortex. So there's a composite object of charged particle and vortices. And with time, we learned that this has a tremendous relevance to the fractional quantum Hall effect. At the time, though, the fractional quantum Hall effect had just been discovered or announced by Sommer, Stewie, and Gossert. He learned by considering just the simple quantum mechanics of these composite objects that the statistics, like their spin, interpolated between usual bosons and fermions. And he had this sort of parenthetical statement I find him using now. Although the practical applications of this phenomena seem remote, I think they have considerable methodological interest and do shed some light on the fundamental spin statistics connection. Less than a year, or about a year later, the fractional quantum Hall effect has been announced. Laughlin has put forth his theory of a quantum liquid of fractionally charged quasiparticles. And Bert Halpern was working on trying to understand some of the daughter states from the principal Laughlin state at 1/3, the hierarchical states. And in the process, he discovered that the quasi-particles, in addition to being fractionally charged, as Laplace had taught us, must have fractional statistics as well. So this was in late '83. And so his statement, which is also interesting, the appearance of fractional statistics in the present context are reminiscent of the fractional statistics introduced by Wilczek to describe charged particles tied to magnetic flux tubes. And of course, with the development of composite fermion theory and all the things that come later, we know that is an important step. So by '84, Rovas and Schrieffer and Wilczek had given a derivation of the fractional statistics that would be more familiar to modern students of condensed matter physics, basically calculating the Berry phase for taking one quasi-particle around another. So my point in showing all this is by 1984, theory has told us that the excitations of the fractional quantum Hall effect must be fractionally charged and have fractional statistics. And the question is, okay, it's 40 years later. What was the problem in trying to measure some of these properties? And that's the story I'll try to tell you a little bit about. Before I delve into the specifics of my system, I do want to mention that many condensed matter systems can be expected to host anions, the quantum spin liquids, the topological superconductors, both the intrinsic and engineered type that I work on, the fractional quantum anomalous Hall effect in graphene layers and TMDs. This is all very exciting work. I think it's a really exciting time to be in this field, because if it were just fractional quantum Hall physics, well, that's not very interesting. So we're really entering an era, I think, where there'll be multiple systems in which anions can be found. And even in the fractional quantum Hall effect, devices in graphene have developed to such a degree of sophistication that they are building interferometers as well. Philip Kim's group, Andrea Young, Yuval Ronen at the Weizmann. So it's pretty exciting. And I'm going to tell you about the old standby aluminum gallium arsenide, because it's the most mature system and it's the one where we can really build fairly complex devices. But again, I expect more to be found in these other systems. So the talk is going to focus on the fractional quantum Hall effect in aluminum gallium arsenide 2-degs. And by now, I think everyone's pretty familiar with this type of transport. This is just bulk transport. The longitudinal resistance is in red, the Hall resistance is in blue. This is a fairly low density sample, 1 × 10^11 per square centimeter at low temperature. And basically, it's just a zoo of states, okay? You know, there's the integers, but there's many, many fractional states. And the technology of the sample preparation has advanced that we're fairly readily can produce samples of this quality. So if you're interested in looking at your favorite composite fermions, you pick here, here's in the n = 0 Landau level, you pick half filling or quarter filling, and then practice the dark arts of wiggleology and count the number of wiggles. If you're interested in potential non-abelian states, you can go into the n = 1 level. Here's the 5-half state fully quantized down at a very low field of 1.8 Tesla, not exactly 0, but getting there, and it's a putative non-abelian state. So, given the time and efforts of many, many groups, the sample quality has advanced where we can see all of these states. But the story I want to tell you, it's not this that enables the observation or the exposure of some of these properties. This has been, this is not new. Doing bulk transport doesn't get at the particular properties that we want to measure. So while this is all nice, it's really not the improvement of mobility or seeing more and more states that's been the hindrance. It's something that's a little bit more complicated, and I'd like to tell you about that. So the take-home message just from this part of the talk is that the excitations of the fractional quantum Hall effect are anions. They're supposed to be fractionally charged and have fractional statistics. Now, the quasi-particles carry fractional charge, and Laughlin told us that back in '83. But it took nearly 15 years with developments of sophisticated quantum shot noise measurements and sample prep and developing good EBL, electron beam lithography for QPCs, until two groups, one at the Weizmann Institute, Moti Heibelum's group, and another at Saclay, were able to measure quantum shot noise and see that the charges of the edges is actually carried in E/3, the units of E/3. The same could be said that Bert Halperin and Wilczek and Schrieffer and Rovas told us in '84 that the statistics should be fractional. In particular, for the Laughlin states, the anionic phase should be 2 pi times the effective charge of that state. And I'm giving this talk now, and it's only in the last few years that we've been actually to probe these properties. And so there must have been something in the way. I'm talking about nu equals 1/3. This is not some exotic higher order state. And so what that was is an interesting story, at least for me, and I'll try to convey some of the details to you. So what do I mean exactly when I'm talking about fractional statistics? Just to be clear, in this little cartoon, these little vortices represent localized quasi-particles. If I take one around the other and bring it back to its original position, you say, well, you didn't do anything. That just brings me back to the original state. Nevertheless, for anyons, a non-trivial phase is developed, and there is a measurable difference between this associated with this braiding operation. So just remember, at the principal nu equals 1/3 state, this angle should be 2 pi over 3. Okay.
I think it will only take a halfway around, right?
Yeah, it's 2 exchanges. Okay. So what I'm talking about here is not the fundamental braid, but 2. Okay. So there is that ambiguity in the experiment we're actually measuring is 2 theta. All right. So you can say, okay, what took you knuckle dragger so long to do this? And the answer is it's hard. And there's physics involved that's not captured in these simple, well, I shouldn't say simple, but in these high-level models, it misses some of the essential physics of devices. And that's what the issue really is. So to really carry this all the way through, there had to be innovations in heterostructure design, device fabrication, measurement. And so, it goes all the way from designing the proper heterostructure. In my particular case, it's via MBE what we go, but the van der Waals people are making stacks, and that's an alternative route. But for us, we had to design the structures to expose the fractional statistics, not just to see the state, but to actually be in a particular configuration that would make the experiment work. And so, it's along this line that we have to progress, and you just don't know starting out. And there were a number of experiments over years by many groups, Charlie Marcus's group, the Heibelum group, and the Weizmann, many groups, where we learned what the mesoscopic physics that could influence these types of measurements was going to be. And that's where we are today. So I'm going to give you the summary. Maybe you can fall asleep if that's all. But over the last couple of years, we've been able to design specific heterostructures that suppress some of the mesoscopic effects that have been obscuring measurement of fractional statistics over the last 15 years. And by careful design of the heterostructure and then building a somewhat complicated device, we're able to first see a bone type interference in the fractional quantum Hall effect. Subsequently, we were able to refine some of these device designs to actually measure anionic phase slips. I'll tell what this is later, but this is the evolution of the Aronoff bone phase, punctuated by some phase slips that are associated with the addition or removal of individual anions. Extract the actual phase, and it's consistent with the phase factor 2 theta, if you will, 2 pi over 3. Now, how are we going to measure fractional statistics? Well, in analogy to our optical experiments, if you're interested in measuring fine differences in phase or want to know about phase, interference experiments are exquisitely sensitive to phase and phase differences. So what we need to do is build the electronic analog of the Fabry-Perot interferometer. and have it operate in the quantum Hall regime. So just for illustration purposes, the blue region is the two-dimensional electron gas. These yellow lines and T's are surface gates that we use to locally deplete the carriers. Of course, we have ohmic contacts to galvanically connect to the two-dimensional electron gas. And we're going to use these surface gates to define our interferometer and induce partial backscattering. So the surface gates define the interferometer chamber and the interference path. And these quantum point contacts act as beam splitters, the one near the source and near the drain. They're the analog of the beam splitter. So in the quantum Hall regime, current is carried by the chiral edge modes. It comes into the first QPC. We control the backscattering and partially backscatter some of the current to the other edge. Most of the current continues on in the interior of the interferometer. We partially backscatter again at the second QPC. Now, the current that circulates around the interior interferometer, and if this transport is coherent, adds to the partially backscattered current from the first QPC, and that generates our interference. So if we're looking at this and considering what current passes from source to drain, of course, there'll be a term that is just proportional to the transmission coefficient squared of the first QPC, a term that's proportional to the transmission coefficient of the second QPC squared. But then there's this interference term. This cosine theta here has to do with the addition of the current along the internal path. Now, this theta is the interference phase. It's not the anionic phase. It's just the phase that builds up in the course of this measurement. So if I'm in the integer regime, I'm dealing with boring old electrons. This phase that builds up is nothing but the Aronoff-Bohm phase. It's proportional to the area of the interferometer times the magnetic field penetrating through. That's the flux, and it will be periodic in units of the quantum of magnetic flux, H over E. So I can operate the device I can measure interference by measuring the electrical conductance across it. I operate by changing the area by these two plunger gates on the side. Think of it as an accordion. I'm opening, squeezing and opening it up to change the area. Or I can change the flux by changing the magnetic field that penetrates through the device. And I'm also controlling the amount of backscattering that occurs at each QPC. Now, the theory in detail of how these things should work has been known for quite some time as well. The proposal that we could use this device dates back to the work of Shimon, Killissen, and Sondy back in the late 90s. And what they told us is that if you build one of these interferometers, you can use it to measure fractional charge, fractional statistics, even Luttinger liquid parameters of the edge state. So if you can get—
Can I just ask a brief question?
Oh, sure. Sorry.
Naive question, but is this formula valid only when T1, T2 are small, smaller than one?
Yes, I'm working in the weak backscattering mode here. Okay, you can get more reflections, and in fact, even this is an approximation. It's a summation over different terms, but when I have weak backscattering, I can essentially approximate it by this.
You probably only care about the cosine, but why does it not vanish if T2 is equal to 0?
If T2, it does go if T2 is 0.
Right, so T1 squared stays there.
There's no interference if I don't backscatter at the second QPC.
Oh, this is only the very.
Yeah.
Backscatter this first one, you have a current.
That's just the current.
This is the current that ends up at the drain, or you can quickly think of the backscatter current. It works. You can go over later. Yeah, okay. So this is the case of just bare electrons, and naively you expect lines of constant phase or constant conductance to have negative slope in the BVG plane. So this is a theory plot. This is from the Halpern paper. If you plot the lines of constant conductance or constant phase as a function of B and voltage, which is the side, the plunger gate voltage, you should get this barbershop pole pattern of lines of constant phase. This is for electrons and no interactions in the sense of we're treating the interferometer as a inert object. Now, it becomes more interesting if I move into the fractional regime and I have localized quasi-particles in the interior. Again, this big spiral represents a localized quasi-particle. Two major things happen. One, the AB phase gets renormalized or scaled by the effective charge. So the periodicity will change in accord with the fractional charge when compared to the periodicity associated with electrons. And then the interference phase, the thing I measure, becomes directly dependent on the number of localized quasi-particles in the interior and the anionic phase. Okay, so if I measure this phase, I have information about quasi-particles. Now, what you might expect is that, well, the quasi-particle number can only change in integers. I add or remove one. So if I had this normally evolving AB phase, and I added or subtracted a quasi-particle, there'd be a jump, a glitch in the pattern. And the size of those glitches, so I'm adding or removing individual quasi-particles, can tell me what the anionic phase is. So this kind of pattern plus glitches is what we're ultimately looking for. Okay, now what's the problem and why wasn't it done, I don't know, 30 years ago? Well, in reality, this simple model I gave you, an analog to optics, took it too far. Photons don't interact, but electrons certainly do. And to build this interferometer, I have to build a little mesoscopic device. I call it interferometer. You can also call it a quantum dot. And the charge on the edges and the gapless edge modes interacts with charge in the interior of the chamber and modulates the interference patterns you can get. So when the coupling between the charges is minimized, you can get the AB limit, the Aronoff-Bohm limit. But as I start cranking up the interactions between charge on the edge and charge in the interior, I can get all sorts of interesting patterns developing. This is just as a function of parameters I'll tell you about in a minute. This is a calculation, again, from Bert's paper. So much so that when I reach a Coulomb-dominated regime, when the charging energy of my interferometer is large enough that is behaving much like a quantum dot, the lines, the AB, what I used to call AB here, are completely flipped. And the importance of this is you say, well, okay, fine, it's just going in a different direction, is if you're in the Coulomb-dominated limit, the anionic phase is unobservable in principle. So if you have too strong interactions, there's no chance of measuring it. Okay, so the theory of all this has been worked out over many years by several groups, but the upshot is that the regime of operation depends on some critical energy scales that I'll talk about in a second. Specifically, the ratio of KIL, which parameterizes the bulk edge interaction, to KI, which you can think of as the edge stiffness, how much energy it costs to add charge to the gapless edge. And depending on the ratio of these, you can get all sorts of behavior. Okay, so KIL, the thing that's interesting to us, parameterizes how strongly it's interacting with the edge in the interior, and KI tells us the cost to add charge to the edge. And if we're in the Coulomb-dominated regime, we simply cannot see the anionic phase. So we want to write it down in this regime. And it took a long time and many experiments by other groups and theory development to actually realize how important this was.
Can you say,
I'm sorry, it actually didn't what and what. You're saying bulk edge, but there should be two objects. K sub IL.
KIL?
Right, yeah.
Okay, so in principle, there's an incompressible interior, and then there's circulating edge currents around. And if I change, say, the charge in the interior.
Uniformly.
Not uniformly, no.
Right, because it's
no, you can't. But if I change it either by introducing quasi-particles, or I do it because I'm still in a fairly open system, I can add charge to keep filling factor constant, the edge can respond to minimize the overall electrostatic energy.
Changing the size of the.
Yeah, if you let me go, I'll explain it, okay? Okay.
But sorry, can you just say it's the first factor? You had the statistical angle plus the trivial AB times the E star over E.
Where do you want me, which
So
one here?
I'm saying the change from interactions that you're about to talk about comes from the first contribution, A, B over phi naught, meaning modification to that first piece.
Yeah, you can think of it in that way.
It's not really doing anything to the thing you're after.
No, of course, it doesn't fundamentally change the anionic statistics. That is,
Right.
obviously, that's not subject to mesoscopic effects, but it modifies what I measure and therefore interpret as the anionic phase. Yeah, it's all in, this is the business end of it, if you
It's
will.
kind of the thing that masks.
Yeah. And if that term is strong enough, that is to compensate for any anionic phase, you get a fact that's just too high and you don't see any slips. Okay, good. Let me press onward. All right. So here's an experiment that happened quite some time ago, but that was sort of inspirational for us. Charlie Marcus was trying to get these things to work, and he made a series of devices. One that was small by standards of the time, 2 square microns, but he had a surface gate on top. He just put a surface gate. His tube egg is buried underneath, and no matter how hard he tried, he always got this Coulomb-dominated behavior in this small device. So the lines of constant phase going the wrong way. But then he did something interesting. He scaled it out and made a really big device where the area is 18 square microns. And again, he had the top gate. Now, what does he get by making the uniformer big? Well, he reduces the charging energy. It's not a small quantum dot. He reduces these Coulomb effects. Now, they were able to get into the AB regime. Okay, there's lines of constant phase with negative slope. But if you see, look at the field scale, it's down at half a Tesla. That's at filling factor 20 or 22 or something like that. I don't remember exactly, but it's way away from the regime you want to operate. And the problem here is while he had suppressed the Coulomb interactions, the device was so big he was losing coherence. There's other technicalities, but you think of it that way, the path length is so long, the edge velocity is going down as B increases, E cross B over B. And so he's actually, the patterns fade away. But it was an important point. You can get AB if somehow you suppress the Coulomb interaction. So to summarize this part, we want small interferometers because they have good coherence, short path length. But the problem is they come with Coulomb-dominated transport, large charging energy. Large interferometers are good because they reduce the charging energy, but they have low coherence because of the long path length. So
Charlie's experiments see the charge, fractional charge, or no?
no.
What are the filling fraction there? In the second one, charge quantization.
The one I just showed you?
Yeah.
20, U equals 20. It's barely in the integer regime. It's Schmid-Hassel, it's in the, yeah. So it's nowhere near where you have to be. It was a great experiment. Told us a lot, but actually, yes.
But these are parallel edge state. What is causing the decoherence?
It can, well, there can be a lot of things that can cause decoherence, thermal processes as well.
It's a kind of, but in interference term. Interference term is very sensitive to any fluctuations.
Yeah.
Energy
if you can potential time.
Time it broadens, and then you're averaging over a different phase. So there's, believe me, there's a million things that can kill coherence and fractional edges.
Okay. Scattering breaks coherence.
Okay.
There are 2 parallel states, but they're kind of propagating.
Okay, can I go? Good. So here's where we are, and here's after Charlie's experiment that got us thinking. And what can we do? Well, he did a good job of making it big. He tried to put this gate on to kind of screen out some of the long-range Coulomb interactions, but it's too far away. Well, we have an MBE, and so we can grow the gates directly into the structure. So, I'm showing the wrong one. So here is the blue region of the 30-inner quantum well. That's where our electrons reside that we want to probe. But on 25 nanometers on either side, we drew 2 more quantum wells that we heavily populated with electrons. Here's in the middle section, you see the conduction band edge that's in red as a function of the growth direction, Z, and the blue line represents the electron charge density. So here's the well that we're going to probe. It has about 1 × 10⁻11 electrons, but close by, we put high density electron gases with different densities, roughly 25 nanometers away. So Charlie's gate, top gate, that was 200 nanometers from the 2-deg, we now have 2 of them 25 nanometers away on either side. That makes it, we have a tri-layer of electron gases, 3 separate electron gases of different density. That's going to cause complexity in the device, but the price is well worth paying because we're going to use the electrons in these 2 ancillary quantum wells to screen the long-range part of the Coulomb potential, not the short range, but the long range, reduce the charging energy so that we can actually work in the AB regime. It has an additional beneficial feature that I'll talk about in a minute, in that it sharpens the edge profile, having these 2 wells nearby. One of the problems in gallium arsenide is it's susceptible to edge reconstruction, and that's a function of the fact that the confining potential can be soft. In this particular configuration, electrostatic simulation shows that the confining potential is very sharp, just like it appears to be in graphene. And graphene, in their structures with their graphitic gates nearby, looks very much like this. We just had to grow it in the MBE. Now we have to go through some fancy device processing, but even still, after all that, with low density 2-degs, you can still have high enough quality that you see strong fractions. Okay, so how does this thing work?
So these densities look very close to the density of the actual system. So it's 2.
No, they're not. They vary 80% and 50%. I put them there specifically so they don't go into a quantum Hall state when the principal well is in a quantum Hall state. They're high, 80% change in density is huge. Two. You have last time I checked.
It's still in the
what?
Twice is the
you don't have the, if they all, I would know if they all enter an integer state at the same time, everything would go insulated. The densities are sufficiently different.
It's just twice. It's like
no, not exactly twice. These numbers aren't random. I didn't, they're there for a specific reason so that we maintain some metallic, I mean, it's not a metal, it's in a field, but some compressibility in the 2 wells around the main one. When the main one is in an incompressible state, you still have compressibility and can screen.
It's not in the integer, it's not the integer state.
Yeah, and they're not integer states anyway. That's right. So as long as I avoid having these guys in big fat integer states, I'm okay.
But also not in fractional Hall states.
Right. Yeah. So there's a lot of designing that goes into that. I'm just showing you the end result. Oh, 5 minutes. Come on. All right. So we have to build a. You're gonna give me a couple more minutes. You got it, okay? I came over in Minnesota, So we make contact on all 3 layers. We don't want to look at transport through all of them, so we have to gate off the transport through the screening wells. The screening wells are still there for the mesoscopic device. I'm just cutting them off from galvanic connections out to the omics. This is a technique that Jim Eisenstein used to great effect back in the 90s for looking at correlated bilayers. We just applied it to tri-layers and mesoscopic devices, and it works. All right. If the experiment works, you can get the graphic department and make fancy looking pictures like this for you. If it doesn't, not so much. What it really looks like, in the end of the day, the device looks like this, and it sits at the bottom of a dill fridge. Now, we can go to nu equals 1, some early devices, and here you see AB oscillations with the expected relationship for lines of constant phase. The upshot of this is that we did it in a device that was 20 times smaller than the Marcus experiment, and the interference is large amplitude and robust. It survives up to hundreds of millikelvin, at least at nu equals 1. Why? Device is small. I'm not being debilitated by decoherence, and the edges are very sharp, so the velocity is higher. Okay, this is a point that's a technical one, but
The Coulomb interaction is weaker because of these two other layers? Or
yeah, screening. The long range part, I'm still many magnetic lengths away from, so I'm not perturbing the fractional state too much, but just the capacitive coupling is reduced. Okay. If we look at the single QPCs and look how they respond, these are sharp quantization and then fall off. We can calculate what the density must look like to produce this. Part of the problem of gallium arsenide, this is not a criticism, it's just the reality of what we have in gallium arsenide usually is that the soft confining potential leads to reconstructions. This is data from another group that's in principle at nu=1. They start out at 1 unit of quantization, that should go to 0. Instead, there's resonances and an intermediate 1/3 plateau, meaning it's soft and they form an incompressible strip of 1/3 on the way to 0. All right, coherence is good. I'm gonna have to rush. We can define the coherence. Now, we take it to 1/3 in the fractional regime with the first set of devices, and here we see the AD oscillations. The periodicity is changed by a factor of 3 and gives us fractional charge. So this was in the first paper, we're able to see the fractional charge, but you note that I don't have any phase slips that may be indicative of introduction or removal of quasi-particles. The field scale is rather narrow. This is a function of the fact that we put the filling factor 1/3 up at 13 Tesla, limits some of the range, but there's also physics involved. I showed this data to Bert Rosauer and Adi Stern and said, well, it looks good that we're getting interference, but there's no phase slips. They came back with a calculation and said, well, our design had overcooked it. We had suppressed the Coulomb interactions so much that we made it energetically unfavorable to introduce quasi-particles. The system would rather introduce charge to stay at fixed filling. So there's a competition between the energy cost to create quasi-particles and the electrostatic cost to keep new fixed. And what they predicted is that if this is the center of the plateau, there should be a transition between the 3 phi-naught periodicity or the in the incompressible region to a phi-naught periodicity when we cross the incompressible to compressible region. Okay, so if you want to think about it in the middle, the chemical potential is separated. There's not many states available. If I move over into where it's easy to generate quasi-particles, the period changes and it does so symmetrically. Okay, you can calculate, they predicted what that width of fixed filling factor would be, and depends on the gap, the filling factor, the effective charge, and the capacitance. We actually compared it to our experiment, and lo and behold, we had no chance. So we went back and redesigned the structures, went to lower density and smaller devices, and here's what the pattern looks like. Now we have the lines of constant phase with negative slope, but you see these glitches. And at first blush, you say, that's crap, it's noise, switchy device. But no, it's actually not. I should mention that already that the periodicities in both B and V are indicative of charge 1/3. But if we look at these glitches or phase slips and do analysis of them, what we find out is that the change in phase across one of these lines is extremely close to 0.33 and does so repeatedly. And for the people who are interested in the details, the actual slope of these lines is related to device parameters. That's not random. So we looked at a bunch of these and did this analysis. The phase slips experimentally came out to be minus 2 pi times 0.31, and our measurement uncertainty for this experiment was 0.04. Theory told us 2 pi over 3, so we took this as confirmation that we had actually been adding and removing quasi-particles with the right statistical phase. Just to convince you that's not just a one-off fluke, we now know how to design the heterostructures in the devices to probe different aspects of it. In a later work, we actually enhanced the bulk edge coupling, which increased some energy scales to make things sharper and allowed us to work not only in the incompressible regime, but the compressible regions. So if you look at this, there's a central region of 3,5 naught. Out in the compressible flanks, there's a complete qualitative change in the interference. It loses magnetic field dependence and the periodicity switches to phi naught, just as it should when it becomes, for every flux quantum you introduce a quasi-particle, the periodicity should now be phi naught. And these little modulations, these little breathing tell us because the AB oscillations it's a continuous evolution, but the addition or subtraction of a quasi-particle is discrete. So these little breathing modes you see here are indicative of anyons even in the compressible regime. Just to zoom in, now the phase slips are quite sharp, and the transition from incompressibility to the compressible region is clear. Okay, so extremely sharp phase slips, clear transition between incompressible and compressible. All right, I'll have to run through this part, but there are many tests you can do to see if this jives with expectations and sanity checks to see if this modeling all works out. There's a central region of the 3,5 naught that's experimentally 480 millitesla of 3,5 naught. If you use Adi and Bern's theory, they predict around 530 millitesla for that range, given our measurement parameters, pretty close. There's the phi naught regions. If I increase the temperature, you can see a smearing out, a loss of, this is a thermal smearing and decoherence, where the quasi-particle number in the interior interferometer is changing on the time scale of circulation around, and so we lose phase coherence. This is as expected. You can look at 10 millikelvin and compare the periodicity out in the flanks to the periodicity at nu=1, where it's phi naught because we're just doing normal electrons. It overlaps in these regions with the periodicity at nu=1. You raise the temperature to 90 millikelvin, gone. Okay, I don't have time to do all this, but there's a lot of analysis you can do now that we have control of the devices to see if our models, the theoretical models, not my models, but the theoretical models of how these things behave actually work quantitatively. And there'll be modification of the interferometer phase, that scattering phase. I gave you a simple formula before, but if I add finite bulk edge coupling, it looks kind of hairy, but it's not that big a deal. You just need to measure independently KIL and KI, and you can relate the measured phase slip to the anionic phase. I'll skip this one in the interest of time. So let's do that. In this region, if we take the average phase slip of what we measure, that's the measurement, it's only minus 0.24, not 0.33. But remember, I've added finite bulk edge coupling. I can extract the bulk edge coupling, this ratio, from the experiment. It's not a fit parameter. It's measured in experiment, about 0.27. It modifies the phase. If you add in that contribution, the anionic phase comes back to 0.33. So we can, tune the devices where we want. And so far, it appears that the modeling and what we see in experiment is holding up. Okay, so let me just conclude. One question they ask is, okay, that's 1/3. You've been doing that for a couple of years. What's new? We can and want to extend to more complex fractions. The daughter states of the hierarchy, 2/5 was the first one we tackled. It's not trivial or obvious that you can do it there. Bert Halperin and Dima Feldman gave us a list of reasons why it wouldn't work, but, or not, I shouldn't say that. There are challenges that must be accounted for. And at 1/5, excuse me, at 2/5, not everything is just the filling factor. The charge is 1/5, the phase is different. So we recently did that at the end of last year and got the correct charge and phase for 2/5 as well, which was a non-trivial extension for us. You have to be able to independently interfere to multiple edge modes and all that kind of stuff. So for conclusion, I think we're at a stage where we can say Fabry flow interferometry can be used to make quantitative determination of anion statistics and fractional charge. We've done it at 1/3 and 2/5, and these techniques can be applied to other material systems. And I think this will be very powerful. The graphene guys are making great progress. and using similar techniques. And I hope to some of these other topological phases that will host anions, similar techniques can be applied. It took us a long time to work it out in gallium arsenide, but once you know what's important, hopefully the progress in the others will be quick. Thank you.
So Mike, you showed the size of the facelift. We go back to one of the 2D plots with the pajama plots.
Give me a second. Which one? Where?
Sure. So yeah, that's fine. So you showed the size of the facelifts, and you also commented on the different regimes of magnetic field. Can you comment on the locations of the facelifts?
In location in what parameter?
In these 2D plots, so they fall on lines that go from bottom left to top right.
That's right.
So they're not sort of discrete jumps where a quasi-particle comes in, and then once it's comes in, it stays for a long time. It seems, I don't know which, presumably you're sweeping gate voltage fast and magnetic.
Yeah, of course.
slope.
So the inner loop is gate voltage, the outer loop is magnetic field. And the fact is that where the facelifts occur are the lines when it's the energy difference between adding a quasi-particle or staying at fixed filling is the same. Okay, so there are particular points in B and V where that condition is met. Normally, you'd expect just AB evolution, but because of disorder, there's always remnant disorder in the system. There will be specific states that have been lowered in energy, so it actually works out to add a quasi-particle there. Now, the slope, I'm not sure exactly what you're asking, but the slope is anticipated and actually can be determined from the lever arms of the gates. So we know
that's assuming that all of these locations are effectively changing the charge in the entire island in some way. And so
no.
Well, so
it means that means they're distributed somewhere in the interior, and the fact that all the lines have essentially constant slope means that the lever arms are more or less constant. So that means it's not necessarily, if you had a defect that was very close to the edge, you could imagine different lever arms.
So that's related to the slope that you get in the Coulomb dominated regime. But you're basically adding a charge. You're adding a quasi-particle, but in total, you're adding a charge for your island.
It's at the, I can show you the equations, it's where the charge is actually constant. Okay. So, and the slope is given by the coupling of the gate to charge in the interior. One of the differences that seems to be emerging between what we see here in gallium arsenide and graphene is it appears that there may be states that are close to the edge so that you're not looking at some average lever arm to the interior of the interferometer, but to a state that's close by, or one that's over here. And so what they're tending to see right now is that these slopes can have any put in different directions. That's not a cure, it just means you have to map it out. But what it appears for us is that the states are more or less uniformly distributed in the interior of the object and not strongly coupled to a particular edge.
Thank Mike. I speak with Radzihovsky, use Boulder, and they will talk about the physical.
Oops, I took the mic with me, sorry.
Yeah. There's like.
Okay, thanks for sticking around. I guess I'm last speaker before dinner. So I also wanted to start by thanking the organizers for bringing us here and actually making the making a March meeting an appealing event. And maybe this could become a tradition. In fact, even if the March meeting is somewhere else, this has been going on so well, then they could do it every year. Andre, although it is in Minneapolis. So when I must have I realized when I saw the program that I must have sometime back when I first was asked to provide a title, given a title that I was involved in at the time, but then I decided, looking at what the mission of the sort of conference was, to give a bit of more of an overview of stocks. I decided to actually not talk about critical matter, but instead talk about another type of matter. And I thank Ethan for actually setting up some of the things I'm going to say, and apologize to some of you who may have, one, are sick of me talking about fractons, and two, maybe were interested in critical matter. On the second one, there's a review article for a book commemorating Michael Fisher and 50 years of renormalization group that's on the archive last year that you can look up if you're interested in critical matter. And for the fractons, most of what I'm going to say is in this review article with Andrei Gromov. The only thing maybe I will say, let me go back. What I was going to say about the critical matter is that it's something I've been studying for years, and there's some modestly interesting recent results that I won't talk about, but it's states of matter that whose ordered states are described by infrared attractive fixed points. So it's critical behavior, but that dominates the whole phase. So you have universality throughout the phase. You don't have to tune to it. All you need to do is respect symmetry of the state, of the ordered state that's broken spontaneously, and then your Goldstone modes are strongly interacting and result in this infrared attractive fixed point, which is quite unusual compared to sort of conventional systems, like think of some conventional sigma model of some sort. Okay, but instead I'm going to talk about different type of matter. And so let me start out just, for those of you who are not so familiar with fractons, it's a strange type of quantum liquids, really, unfortunately, so, for the most part, are limited just to models. And these claim to fame of these models is that quasi-particles in these systems have restricted mobility. As indicated here, they have various dimensionalities. Kind of the most important one is called is the fracton, but then there's other ones that are subdimensional particles that some models display and others do not. So quite broadly, these models fall into two types. There's sort of discrete symmetry type models based on, let's say, some Zn. So for example, X cube model. And then there's models that, so these tend to be these are lattice models. And then there's sort of another route to fracton systems introduced by Michael Petko, pointed out by Michael Petko, is through, these are gapless fractons, and this is through kind of novel type of gapless gauge theories. So I will discuss that and mostly focus on these. So, these models share many interesting properties, exponential and scale-dependent ground state degeneracy, non-existence of deformable line operators, which is what is responsible for this restricted mobility, And there's a very strong lattice dependence. Sometimes this is called UV-IR mixing. So it's somehow these models are beyond, they don't have a nice continuum field theory limit. So, this approach to them captures some aspects of Flackton order, but not all. And so part of the story is try to understand, is there a field theory description and an RG description that we're so used to in conventional systems. So, as a motivation, for a few decades now, people have been studying, looking for beyond Landau symmetry breaking paradigm physics. And, that there's been a lot of models, and although, experimental smoking gun is still absent as far as I understand. But, there's been many models that demonstrate this sort of what I call conventional quantum liquid behavior beyond this Landau paradigm. So the kind of systems I'm going to talk about are these fractonic models that sort of beyond this conventional quantum liquid paradigm, as I described in the previous slide. So in terms of motivations, first fractonic model that I'm familiar with was by Claudio Cimone in 2005. And he was motivated by trying to construct a model that has glassiness, slow dynamics, but without quench disorder. And in retrospect, with the renaissance of fractonic model, studying fractonic physics, it was appreciated that, that original model that Claudio proposed is actually one of the fractonic models. Then I think the field sort of took off, keep mixing up the knobs. The field sort of took off with Haas work on trying to construct a robust quantum memory, finite temperature memory. But then, there's many other proposals, but the idea is to construct, the goal is to construct ever more novel quantum liquid systems that with rich ground states and constrained dynamics, as the kind of stuff that you heard from Ethan. And I'll mention some applications. So before I delve into sort of specific models, I wanted to just kind of take a bird's eye view of trying to see where this kind of physics can come from, at least in the continuous symmetry case. So you start out with a system that has some charge conservation. So this is a continuum equation for charge. And then in order to build in constrained dynamics, one way one imagine doing it is to introduce multiple conservation. And in terms of this continuum equation, it's very simple to do, at least, sort of mathematically. You have to design a current that is a derivative of another higher rank tensor current, as illustrated here. So for example, if n equals to 1, then you have the charge current is a derivative of a tensor current, two-index tensor current. So then you have, in addition to the charge conservation, you also have dipolar center mass conservation. Okay, because of, as who was talking about it, integrating by parts twice, you can get both of these monopole and dipole to be conserved. So there are various models that simple models, although some of them are fine-tuned, that display this behavior. So Ethan talked about tilted particles moving in the tilted potential that were realized by Vakar and company. One can also think about lowest, not lowest, but just if you consider hydrodynamics within a Landau level, there is an effective dipole conservation there. In fact, if you look at the continuum equation for momentum violated by Lorentz and electric field terms on the right-hand side, then and look within the guiding center approximation dynamics, then indeed you'll get that. Well, so the tensor you will get is the TI energy momentum stress tensor, and you can eliminate the charge current in favor of a derivative of the energy momentum stress tensor. And so now the continuum equation for the charge will end up being the second derivative of a current of the energy momentum stress tensor. And so indeed you'll get this kind of dipole conservation. Also, vortex liquids have very similar dynamics. So in terms of simple models, so Ethan already talked about sort of this model that conserves dipole, has a dipole conservation. There's a lattice model. You destroy two particles, you create two other particles, but the dipole, the charge doesn't move, center mass doesn't move, but the dipole, you're creating dipoles. Dipoles are hopping around in such a way that the overall, you're adding quadrupole, but the dipole doesn't change. In the continuum, it's nice to have this thing in the continuum just becomes a Lifshitz model, and it's dipole U1 symmetry is now phase shift, but that is not, it's not unlike gauge symmetry or gauge redundancy where you can shift by arbitrary phase, or unlike purely global U1 constant shift. Here you can shift by a constant phase that is not only a constant, but also varies linearly with the spatial dimension. Even more, so these models are quite fine-tuned, but there are systems like this tilted potential where it arises from energy conservation or some other kind of an emergent dipole conservation. Even more fine-tuned are these models that are still interesting to look at, models with subsystem symmetry. So you imagine that we have charge, which is conserved on foliation, on the leaves of some foliated system. So for example, you can imagine a model in which every charge on every row and every column is independently conserved. So you have an extensive number of charge conservation. So these are the quantities defined here, and then these guys are really zero and don't change in time, and they're independent on every row and every column. And in fact, this kind of a model goes back to Permaconti, Balens, and Fisher. And you can think of, if you think of the microscopic sort of lattice model, it's a Planckian XY lattice model, which has this kind of a dynamics rather than hopping. You have ring exchange like dynamics, okay, around a individual Planckian. So in a continuum, this becomes a Lifshitz-like model, but unlike the previous one with dipole conservation, it has much richer symmetry. The subsystem symmetry is that you can shift the phase by an arbitrary function of x plus an arbitrary function of y. So it's really, again, extensive number of conserved charges. Okay, so so this just gives you some flavor of systems that have this kind of a fractonic or restricted mobility, but they're not generic, and they're kind of in some sense sick in the sense of having this very extensive number of conserved charges. But this field has developed, at least on the theoretical side, quite dramatically, and there are many, many constructions.
But I thought in the Permaconti model, even if you add a term that violates the subsystem symmetry, they are formally irrelevant, or not true?
Because phi fluctuates so strongly, you're saying, right?
I've heard that claim. I don't know what the answer is.
Okay, let me. I can't.
The answer is probably no, but there's a lot of details in how the works out. I can tell you about it.
Yeah. So so there's lots of sort of constructions. This is just a very partial list at this point, starting with BJ, Ha, and Fu, dualizing a Planckian Ising model to give you an X-cube model. And in fact, if you are interested, to learn about the subject, this is a very constructive model to work through. You can just understand everything about fractons, at least of of this type, from this model. It's very beautiful and very simple actually to work out. And there's all kinds of other constructions, couple layer construction, couple chain construction. But what I'm going to focus on for the purposes of this talk is this higher rank tensor gauge theory, which goes back to Michael Pretko, or at least observation that these kind of gauge theories have fractonic behavior goes back to Michael Pretko in his seminal paper in 2016. So even before you talk about fractons, you can just ask, what are these? You can discuss these objects, these tensor gauge theories, symmetric tensor gauge theories. So what are those? Well, they're very similar to, they have the structure very similar to conventional electricity magnetism that we're familiar with. The Hamiltonian is E squared plus B squared. Well, in the Hamiltonian language, E is a canonical conjugate to vector potential, and B is derived as some kind of a funny curl of a vector potential. And the new thing is that E and A are not vectors, but tensors, 2 index or 3 index or 4 index up, right? But otherwise, this up to this point, the structure is quite similar. And then there's Gauss's law, you can show that this Gauss's law commutes with this Hamiltonian. And the Gauss's law very naturally, I mean, there are many choices that defines the model, but the scalar charge theory Gauss's law, you have E, which has two indices, so it's very natural to take double divergence of that electric field to give you scalar charge. That scalar charge is going to be a fracton, and it's very simple to see. And in fact, this is what Michael Pretko's contributions to appreciating that this ingredient is really at the heart of this fractonic order or fractonic restricted mobility.
Right, just a question of my ignorance. Should I think of this AIJ as generating like a Wilson plane instead of a Wilson line or something?
How
do I think of it as a gauge there? What is B?
Yeah, I mean, that's right. So it's you can think of it as describing a motion of a Wilson line along I, but carrying a dipole pointing in a J.
Okay.
Okay, so you have the object that's for which you can write a Wilson line, a basic object is a dipole, and that dipole has a direction, so that's the other index. It's sometimes convenient to actually think of one of the indices, not have a symmetric tensor, but to have one of them as a flavor and the other is the space part of the space-time index. Then that flavor is just the flavor of the dipole that you're talking about, and then it becomes much more similar to conventional gauge theory. Okay, so yeah, so as Michael pointed out, this conservation of charges and of dipoles is at the heart of the fractal phenomenology. So the key point is moving a charge changes a dipole moment. So it's forbidden by dipole conservation. So then you can have this cartoon, the charge tries to move. That's the same thing as adding a dipole. Since dipoles are conserved, you have to add an opposite dipole. That dipole is gapped. And so then this process is not allowed. Okay. On the other hand, dipoles may be able to move, and that depends, but it may be in some restricted way, and that depends on the details of the theory, of the kind of theory you consider. Okay, so one question one might ask, and this is what I was interested in when I first heard about these kind of theories in 2016, is, is there any physical realization? What's the simple physical realization? Or in fact, more specifically, I noted that, I noticed that there's some similarity to something that's quite familiar from topological defects in elasticity, in particular dislocations. So what I mean by a quantum crystal, let's say, and I'm going to focus on 2+1 dimensional quantum crystals, it's just, just a bunch of coupled harmonic oscillators. And so then what are the topological defects? What are disclinations, dislocations? And what's quite well known is that dislocations have this constraint that they have an easy time to glide, but they cannot climb unless you have vacancies and interstitials around. So at zero temperature, or even at finite temperature, transport of dislocations is very anisotropic. So then naturally one can, and disclinations are dipoles of the, dislocations are dipoles of disclinations. 7 and 5 pair, for example, the triangular lattice makes a dislocation. And so it's very natural then to think about if these dipoles are like constrained dynamic particles, then these guys would be like fractons, and these are the dipoles. So that would suggest that there's some immobility of dipoles, of disclinations. And in fact, that's what the mapping that I'm going to put forth shows you that disclinations are immobile. But in the retrospect, one can understand immobility of disclinations in a very simple way, having understood it from this mapping. There's a much simpler way to understand it. Is just think about a disclination as an end of a finite array of dislocations, very much like a charge and made up of a line of dipoles. Then if you want to move a disclination, what you actually have to do is you have to add a dislocation. Okay, it's adding a dipole. But a dislocation in terms of atoms, the microscopic degrees of freedom is an extremely non-local object. It's adding a whole array of atoms. So that's not an object that's going to be, that's not an operator that's going to exist in your Hamiltonian naturally. That's made up of, local Hamiltonian is going to be made up of hopping of atoms, not hopping of dislocations. And so that's kind of how you can understand that this process is not allowed, and therefore disclinations cannot hop. So, but to understand a little bit more rigorously, it's nice to construct a theory in which there's a quantum dynamics of both elastic modes, the phonons, and topological defects. And so the natural way of doing that, we know from this very familiar duality, boson vortex duality. So for example, if you want to describe superfluid, there's a standard way of describing it, in terms of phase and the currents, but you can also describe it in terms of, so there are two types of degrees of freedom. There's currents, and then there are vortices. And vortices is singularities in the currents. And so in fact, if the current is a gradient, of the phase, so this is really tells you that phase is not a single valued function. For vortex, curl of a gradient of phi is non-zero, and that tracks the vortices. And so the Hamiltonian is very simple. It's just the current squared plus kinetic energy squared plus potential energy squared, and these guys are canonically conjugate. But what's nice is you can just rotate these arrows and define an electric field which is perpendicular to J everywhere. So then this law becomes just a divergence of the electric field, where the electric field is rotated, 90-degree rotated current. And so this becomes Gauss's law. And this Hamiltonian naturally goes over to just electromagnetism. The charging energy n squared is just the flux squared. And so that keeps track of flux, keeps track of the number of bosons. And electric field is just the squared, is just the kinetic energy of the bosons. So it's very natural. This is kind of an intuitive way of doing this duality. So now if you think about crystals or elasticity, in the real sense, a d-dimensional crystal is just decoupled XY models, coupled in a very specific way, but nevertheless, it's a bunch of XY models, one for every displacement of phonon in every direction, in each of the directions. And so here's the XY model. So now you have an XY model for every phonon. So this is how one should think about elasticity, or one way one can think about elasticity. There's some elastic constants that encode symmetry of the crystal, but nevertheless, this is the bunch of XY models. So then one can just take advantage of this simple boson vortex duality or XY gauge theory duality to do this for these coupled XY models. And so when you do this, what one gets is this dictionary. So the elasticity part with disclinations and the pairs of disclinations, namely dislocations, maps onto tensor gauge theory. Exactly the kind of tensor gauge theory that Michael Pretko identified as having fractonic restricted mobility. And just to highlight some of the mapping, so this guy just becomes naturally, momentum of the particles maps onto a magnetic field, which is now a vector. Strain or stress maps onto the electric field tensor. The condition of disclination density, which is double curl on the strain tensor, giving you disclinations, maps onto this double divergence of the electric field. Dislocations map onto dipoles, phonons described by gauge modes, strain tensors like the electric field, et cetera, And the key thing is, so for example, the continuity equation for momentum just maps onto Faraday's law, becomes basically Bianchi's identity. In addition, for example, very simple thing like Peach-Kohler force, which is like a Magnus force, but on a dislocation rather than the vortex, maps onto just a simple Lorentz force, or E dot P in this gauge description.
So in this elastic theory, it's a fundamental group still displacement field, or is it the stress strain?
No, so it's fundamentally described in terms of strain, in terms of displacement field, which vector field. That's right. Which is why there's this condition that you have singularities that dislocation disclination is described in terms of defects of this displacement field. That's the elementary field.
So you mentioned Magnus force. I just not familiar. So Magnus force usually is a sample function of velocity, right?
So Magnus force is sort of you can think of it as a force. It's really okay. There's a point of view of it, thinking of it as a force, If you think of it as a force, it's a response to having some superflow. But superflow is a gradient of phi. Okay, so you have a gradient of phi and the response vortices move.
Okay.
Here you have a gradient of u, which is strain.
Okay.
And dislocations move accordingly. And in fact, that Peach-Cold force has, is a vector generation of that. The other thing you see is there's for example, Ampere's law instead of Faraday's law. That just corresponds to this nice equation, which is a breakdown of the vacancy interstitial continuity equation. And so ND is the vacancy interstitial defect. It basically says that if dislocation moves, and it moves perpendicular to the Burgers vector, or in terms of dipoles, dipole moves along the dipole direction, they'll create vacancy interstitials. That motion is exactly the Klein motion that's forbidden. So if your vacancy interstitials are gapped, then you cannot climb. The left-hand side is 0. If you have no vacancy interstitials, then the right-hand side will be 0, so you have no climb. So that's the condition of glide-only constraint. And that is encoded nicely in terms of this Ampere's law. So there's another formulation that I like very much that I'm more fond of, actually, and this is, it has been written up with a paper in 2020 with Mike Kermely, and that's really taking seriously that the elasticity is actually a bunch of coupled XY models. And in fact, there's even a more faithful description, if you wish, where it's D+1 XY models. Well, okay, I shouldn't really say D+1. Let me just focus on 2 dimensions. So it's really 3 XY models in 2 dimensions, namely 2 phonons and 1 rotational degree of freedom, local bond orientation. And those 3 XY models are coupled together. You can convince yourself that this description exactly encodes this. So there are phonons U, 2 phonons and corresponding momentum. And then there's a single rotational field, which would be a Goldstone mode if there was no translational symmetry breaking. Here's the canonically conjugate angular momentum. So this is quantum XY model, this is quantum XY model, and they're coupled in this funny way where the rotational Goldstone mode theta gauges the translational phonon degrees of freedom. Okay, so that's the coupling that reproduces conventional elasticity if you look at low energies. Okay, why is this convenient? It's because then, in terms of this description, you're very close to the vector gauge theory description, because now you really map these 3 XY models onto, you do conventional boson vortex duality, you get 2 vector, you'll get 3 vector gauge theories, but they'll be coupled together in a very special way, such that to give you fractonic order. And so, you get through this. I think I'm, going a lot slower than I expected. So then, but the end result is you get Maxwell-like theory, which has 3 gauge fields. There's a little E field. So that has a conventional, here's E squared, here's a curl A squared. Then there's a 2 capital E and A that has Maxwell Hamiltonian, but they're coupled to, and so capital A couples to the dipole moments, and little a couples to the charges, which is the disclination. These are the dislocation currents. These are disclination currents, and they're coupled in this funny way. Curl of A is not gauge invariant, and it's actually minimally coupled to antisymmetric part of Aij. Okay, so this is okay. So here are the Gauss's law. So there's Gauss's law for each of the 3 gauge fields, and so everything works out here. So the key point is that, for example, you get lots of nice compact way of encoding what we already know about elasticity and topological defect in this gauge theory. So, for example, you get this continuity equation for dipoles. So dipoles or dislocations is pk. So that continuity equation is violated, and it's violated by motion of disclinations. So when the disclination moves, it creates dislocations. So then, thereby, violating this conservation of the dipoles. But another way to think of this equation is that if you have no dipoles around, if they're gapped, then right-hand side will be 0 as well. And that's just a very economical way, very efficient way of encoding it, encoding the immobility of disclinations, namely, their fractonic nature. The fact that you have this continuity equation. And that just comes from generalized gauge invariance of this new type of a Maxwell theory of these 3 coupled gauge fields. Okay. Okay, just a sanity check. if you take this theory, either tensor gauge theory or coupled vector gauge theories, and you look at it in electrostatic limit, finite temperature, no quantum dynamics, just look at the scalar potential part of it. Let's call that scalar potential phi. Maybe the better choice would be A0 from the other theory. And you ask, what do you get? You just simply kill all the time-dependent terms, all the dynamics, and just look at the scalar potential. So electrostatics. What you get is this cute theory, has a, it's a Laplacian-like theory for phi, for the scalar potential. And there are two cosine terms, so it's some kind of a generalized sine-Gordon model with two cosines. And then you could ask, well, what does it describe? Well, in fact, it describes the famous Kossler-Saros, Halpern-Nelson-Young field theory or transition, melting transition from the crystal to a hexatic to a isotropic phase. And so this is kind of cute. So let me just quickly go through this, but it's much easier to understand than doing Coulomb gas pictures of Halpern and Nelson and Young. So it turns out, because this is a Laplacian, this cosine that describes the dipoles charges, and this describes the charges, this guy is irrelevant. The charges are irrelevant. That's just a statement that disclinations don't unbind inside a crystal. And so then you really, this model at low temperatures, when these guys are small, just reduces to dipoles and this guy. So it just becomes this, where I purposely skipped all the indices. And so then in this parameter space, disclinations are irrelevant, and that's these flows. This is a function of temperature. And dislocations can have a phase transition, unbinding phase transition. Okay, so that's but in terms of a variable d phi, this is just a standard sine-Gordon model. If you squint and don't worry about indices, it looks like a standard sine-Gordon model, but in terms of the gradient of phi. And so, but now once this location unbind, this cosine d phi just becomes d phi squared. And that gives you standard elasticity of a sine-Gordon model. And beyond a screening length scale, once this guy has plasma of dislocations, you now can restore this guy, which can become relevant, beyond a certain critical point. And that's the hexatic to isotropic liquid transition. So that's just a sanity check. Now you can, emboldened by this check mark, you can think about a quantum version of this. So you can ask about condensation of dislocations, and so that would describe a crystal to superfluid hexatic transition. And so that has a nice description. It looks like a superconductor where the matter are dislocations. And there's two types, psi k is psi x and psi y, two types of dislocation, let's say, in the square lattice. And then the Maxwell term that I described before, it's supplemented by this Maxwell term. So it's some kind of a funny superconductor with a funny Maxwell term. And so you can go through this and basically construct a phase diagram where phases that are familiar from just thinking about both elasticity and its quantum version and includes supersolid, commensurate crystal, superhexatic. Those phases are just nothing more than the Higgs transition. The transition between them is just the Higgs transition of this model. Okay, which we understand, it works very well to describe phases, and the transitions are well described at a mean field level. So now you can, okay, so that's one type of melting you can have. You can also motivate it by a variety of anisotropic states that one finds in nature or in models. One can then ask about quantum liquid crystal transitions with this view at things. And for example, in particular, think about stripe phases and see how one goes from a crystal to a stripe phase and from a stripe phase state to isotropic or pneumatic state. So I think I'm going to have to just skip through it, but basically you can repeat this kind of a construction where rather than a crystal going to a hexatic, a crystal is going to a layered state like a quantum smectic, and then a quantum smectic goes to quantum pneumatic. And the way that is done is, again, through this kind of a Higgs transition. There are basically two types of charges describing dislocations. Those charges can, when both of them condense, you get a hexatic. When one of them condenses, one of the two condenses, let's say on the square lattice, then you get anisotropic smectic state. And what the way it works is when one of them condenses, then it gaps out one of the gauge fields and then gives you a gauge theory for the smectic that it's given here. Okay, so one can do all that, and one can deduce all kinds of interesting properties of restricted mobility of dislocations and disclinations in the smectic. Well, so let me just in the last couple of minutes finish with some just pointing out some things one may think about. So we, as I said, we have this nice gauge theory that describes, quantum melting of a crystal into various liquid-like states, either fully liquid hexatic or into a smectic state. But we understand the phases very well, but we don't really understand the critical nature of these, the full quantum melting criticality. And what I mean is, if you think of this as a superconductor, what comes to mind is really repeating Halpern-Lubensky model-like analysis of the normal superconducting transition for these kind of generalized gauge theories. And so one can do this for, well, this has not been done, but it's one of the questions that I'm thinking about. It looks quite challenging. The other direction is to think about time reversal broken states and thinking about quantum melting there. And there, these sort of quantum Hall smectic-like states come to mind. And so one needs to understand there's a variety of phases one can consider: Wigner crystal, commensurate smectic to incommensurate smectic transition, pneumatic composite Fermi liquid, and isotropic composite Fermi liquid. So in principle, this approach should give you a way to faithfully describe, some of these phases and phase transitions. So I'll just finish with this laundry list of directions. There's all kinds of, you've heard from Ethan, but there's all kinds of work going on, particularly Andy Lucas's group on generalized hydrodynamics of fractonic liquids. And you get all kinds of interesting anomalous dynamics beyond diffusion. And often hydrodynamic nonlinearities are relevant. And so then you have breakdown of hydrodynamics, which is pretty interesting. You can also think about elastic sheets and various defects in those elastic sheets. Those have admit being elastic and having defects have this fractonic description. There's also very nice work by Bobo Chakraborty on fragile amorphous solids. So think of granular material where you only get elasticity by compressing this object, this, let's say, grains of sand. And so then under a certain compression, you end up getting shear moduli. And so the condition there is that, if you consider a grain of sand and its surrounding, that there's a static equilibrium, which translates into the divergence of the stress. A local stress has to equal to the external local forces acting on it. But that looks like a Gauss's law. And so Chakraborty and company were able to describe this in terms of vector charge tensor gauge theory. I'll skip this animation stuff, which is actually pretty interesting. One can think about experimental signatures. And in particular, Chakraborty studied compared to experiments, the stress-stress correlation function, and saw this fourfold pinch point singularities in these experiments. So that's a nice manifestation of this mapping into the extensor gauge theories. Okay, so I've already mentioned these potential realizations. So let me just close with flashing up a summary of what I talked about. And thank you for your attention.
I have a simple question. This wonderful phenomenology. Do we have microscopic models that show what you show? Quantum smectic, quantum pneumatic?
So, well, okay, depends on, so, the original lattice models that I mentioned, for example, the X-cube model, that's perfectly microscopic in the sense of, well, it depends what you mean by microscopic, but there's a well-defined lattice model. Everything's well-defined. It's not, you don't have to appeal to any field theory. So, but you mean, do I have a microscopic model that has these phases in them? Well, okay, so we know, for example, this is motivated by Jim Eisenstein's experiments. If you have a very high Landau level half filling in the large n limit, meaning nth level, Hartree-Fock state of n plus 1, n plus 1 stripes, I believe is an exact ground state. That was shown by Mosner and company. Okay, so now you can depart from that. You can say, okay, that's a Hartree-Fock theory. Now let me describe the sort of quantum version of that where there actually you go beyond Hartree-Fock. And so motivated by that, you get a theory, and this is McDonald and Matthew Fisher constructed a theory where all the degrees of freedom are there in terms of chiral edge modes between these stripes, both the sort of the width of the stripes and the undulation of the stripe, the symplectic phonon, if you wish. So in principle, those chiral edge fermions or bosons are there, and they describe all the degrees of freedom. And that's what gives me some hope that if I melt that object, I should be able to produce a quantum Hall pneumatic, which, at some point, Alan Dorsey and I studied, which has, fermionic as well as bosonic degrees of freedom. So it should have fermionic degrees of freedom from melting, which one can imagine come from, sort of particle Hall excitations of this thing when you melt it, or vacancy interstitials, if you wish, which are pairs of dislocations. Plus, you'll have some orientational degree of freedom, which is the orientational degree of freedom of the pneumatic phase. So with Alan Dorsey, we just had the pneumatic part, and we couldn't get the fermions. And so the hope is that from melting starting with the Fisher-McDonald model, you can get the fermions as well.
So if you start including, if you go back to the elasticity and you go away from isotropic, for example, include think of as a triangular system where now the acoustic and longitudinal phonons mix along directions and so on. Is there anything there that would give rise to some interesting phenomena in the fractum, or you lose completely the analogy?
You mean systems in which there's no rotational symmetry?
Correct. Yes. Well, I mean, the six-fold you get the same, right? You don't need to have
right.
Full, right?
Yeah.
I'm trying to break it further. Yeah. So in other words, breaking the rotational symmetry, what is the effect in terms of fractums, or is not really meaningful?
I don't think it's that important. So there's really two rotational symmetry. There's rotational symmetry within the crystal, right. Intrinsic index space of the crystal. So that's the one you're breaking. Then there's the other rotational symmetry. So that one's broken in an ordinary crystal. Okay. The other one, and so that one's not essential. You're just going to make elastic constant tensor, fourth rank tensor, not trivial one that I took, not two elastic constant Lamé coefficient.
Yeah.
There's another rotational invariance that you may mean. That's in the target space. For example, putting the thing in a substrate.
Right.
So that one you don't want to break, because then you're not going to have disclinations are going to be, are going to have even higher energy. And so that one is crucial not to break that. But the one of a conventional crystal is not, that's not important. That one you can have, and still this all goes through.
Start thinking about the quantum mechanics of these crystals. Where does the statistics?
What is what?
Statistics. When you start thinking about quantum crystals.
Well, so the statistics comes in that everything I've talked about are bosons, so then they can both condense. So everything has a trivial bosonic statistics. And so in fact, one of the open questions is like, are there more interesting versions of this where you start with fermions, or maybe more interesting Berry phase terms, flux attachment, or something like this, where you get in the end is some kind of a non-trivial liquid when you melt this. Yeah. So that's an open question as far as I know.
Yeah, just an entry question. You show some experimental data towards the end of measuring the correlation function between.
Yeah, stress correlation function.
How is that experiment measured?
So here.
Yeah. So what kind of
So it's really like you have a container with, sand or some granular material. And they measure. They can image stress through the layers of this granular material, and so they can extract data sigma j, local sigma j, as they create this fragile solid by putting pressure on it. So then at some pressure, you develop shear modulus, and then they can image really sigma j as a function of position. And then that data is extracted, and then numerically, this correlation function is computed.
Yeah, so I'm asking about like the electronic system. So we measure electromagnetic response. It's really electric field couples correlation, which is dipoles.
Mm-hmm.
That's not so easy to come up with probes that couple to this higher moments.
Yeah, no, here it's just a real space image. Yeah, they can just measure all the forces and all locally.
Okay, so let's thank Leo.